Hey everyone, so I'm going live a little bit early today. I'm hoping on finishing all the lectures today, this afternoon. I've got 3 left, so I should probably finish by the end of this session. I also went out and bought another notebook. I was running out of paper, which is a good sign. It's a challenging class because I've had to make a lot of notes, working through a lot of problem sets, doing a lot of this and that. So we got 3 lectures left. We just finished, this was lecture 21. Obviously, there's more than just doing these lectures. So just having finished the lectures is just starting the process. I'm thinking, yeah, if we finish today, then that means that I spent probably maybe 4 days on the lectures. Was it 4 or yeah, probably 4 days in total, maybe a little less on the lectures out of the entire month. So I'm thinking that 4 days on the lectures, that's about the proportion that I'm going to need to learn this properly. Now, this is a hard class for me. Part of the reason I picked it is because I wanted to pick something challenging. Obviously, I could pick something where it was going to be easy for me and you'd just see me doing well the whole time. But I wanted to pick something that I was going to struggle on, something that involved relearning, something that involved maybe not having all the right prerequisites, because I thought facing a harder challenge would be more illustrative for what kind of studying techniques I advocate and how I think about these learning hard problems than me tackling something that will be easy for me. The flip side of that is that there's a higher probability that I will not be successful. So if you pick a harder challenge, just all else being equal, there's a chance that you will not meet said challenge. So it doesn't mean that every single challenge that you could possibly undertake is doable within a set period of time. I often, when I'm picking my challenges, I try to pick them so that they will be the appropriate length. One person who I was talking about with this challenge is like, you know what, that sounds good, but it would be better if you could do it in like 1 week. And, you know, maybe it would be better if I could do it in 1 week, or it would sound better if I could do it in 1 week, but I can't do it in 1 week. I'm not strong enough in this particular topic to do it in 1 week. Now, that being said, I did do some classes in about that amount of time in the MIT challenge. So I don't want to give the impression that any particular learning challenge can be infinitely squeezed into some set of time. My goal is just to be effective and efficient when I'm doing things. So I have a particular approach, a particular philosophy for tackling these kind of classes, and I've been trying to articulate it over the past like week and a half or so. How I think about these problems, how I think about handling something where, wow, this is hard, this is difficult. And I'm trying to showcase that a little bit over this period. Now, I know that watching these videos, it can be kind of hard to know exactly what I'm doing, exactly what I'm learning, you know, what the heck's going on. This morning, I got some comments from people who, like, this is, you know, they're watching me watch the lectures and saying this is way too fast. I don't understand anything that's happening. So I'm hoping to try to summarize and condense the techniques. My hope for doing this live stream project was just that I didn't want to omit anything. I didn't want it to be, you know, me giving you some highlight reel or some summarized, sanitized version of what I actually did. I wanted to show that this is exactly what I did from start to finish. And so I'm going to try to go over at the end how I approach things and some of my opinions. And I've been trying to, as I've been going through, kind of reflect on my thought process. So when I make decisions about I'm going to do this many lectures or do the problem sets or do this technique or do this, I've been trying to articulate that over the process. And a couple things that you might notice if you have watched this whole thing is that it's fairly simple. I'm not doing a million different things. I'm doing a few things, and that my decisions are kind of motivated by making kind of a rational analysis of different trade-offs, and so you're balancing different things. So it's not the case that I'm using tons of crazy techniques. I don't think that my approach to studying this would be terribly surprising for a physics student, but at the same time, a lot of people would, I think, look at a class like this where it's hard and they haven't mastered all the concepts and they don't have a teacher and they can't get feedback and this kind of thing and not be quite sure where to start. So I'm trying to sort of go back and try to articulate my own thought process of that, even when it's obvious, even when you're spending time, you know, first start watching the lectures and first do this and making these decisions. So we're near the home stretch of doing the lectures. I got 3 left. I'm going to try to push through them right now. We'll see how much time I have at the end of today. I didn't get a ton of sleep last night. I'm cat sitting for a friend right now, and it's the first night the cat was at the house, and it was meowing a bit in the nighttime. So I am I'm still a little bit groggy, still have a little bit of caffeine keeping me awake right now. And so we'll just see whether my focus drains. If it's really draining by the end of the day, I might call the session a bit early to compensate from the fact that I'm starting early. But if I'm feeling good, I'm going to push right till 5. And if I get all the lectures done, I might go back and go through some Feynman techniques. I might go back into the problem sets. I haven't really decided yet. If I'm feeling a little bit on the fatigued end, I might do Feynman techniques because they're a little bit less mentally demanding than the problem sets, at least at this level right now. And so I might focus on a few of the concepts or conceptual points that I was glossing over when I was doing the classes. Alternatively, I might even just look at the problem sets to try to get a better feel of it, because if you recall from last time, what I did is I covered the problem sets, then went through the lectures, and then did the problem sets. Now, I didn't do this for the second half. There's no real reason for that. I think it was just largely because I wanted to get some sense of the problem sets in general. And obviously I haven't covered all the material, but I wanted to get some kind of flavor for like what kind of questions they were asking. So having done that now, I didn't feel like it needed to have that prep, but I might do that before I start working on the problem sets. So I'll just review all the problems. So I'll just sort of decide once I finish these lectures what I'm going to do next. And Steve, thank you for watching. I mean, these are recordings are going to be available, so it's possible that there'll be more than one person watching later. But I'm not really doing this just so that, you know, obviously 1 or 2 people watching me study. The goal in the end was just to try to document the whole process. So when I did the MIT challenge, for instance, 0 people were watching me live, and I still think that was a worthwhile project. So again, yeah, if anyone's here, if anyone's listening, you can ask questions in the chat. I will try to answer them. I don't promise I will answer them promptly. I'm going to try to focus on the lecture. But if you put them in there, I'll try to do my best to respond. And you know what? I'm just going to quickly put the lecture videos just because I have gotten questions about it. Hold on a sec. All right. So I'll just put those up here just in case anyone's coming a little later and they want to know what we're learning. So let me jump over and let's continue with lecture 22. All right, 3 left to go.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Hi, everyone. Screen has regressed. We're gonna have a guest at the end of lecture today, which should be kind of entertaining. Just as a warning, if you see someone coming. So, question before we get started. No questions about anything? Nothing? Yeah. Yeah. Okay. Let me go over that. That's a good question. So the question is, what again is the significance of the crystal momentum? So, let me answer that in a slightly backward way. So this is a form of the explanation I haven't used. It's going to be a silly one. Let's get back and think about the momentum and ask what the momentum is. Now, you guys showed on a problem set the following fact, that if you have a wave function, psi of x, such that the expectation value in the state psi of x in the state psi is equal to x naught, and the expectation value of p in the state psi is p naught hat. Then if you want to change the momentum, increase the momentum by h bar k, the way to do that is to take psi and build a new wave function, psi tilde, is equal to e to the I kx psi of x. And then the expectation value of x is the same, psi tilde, of x naught, because the space goes away from the two complex, from the wave function is complex counting point to the inner product. But the expectation value of momentum is shifted, in this case psi tilde, is shifted by h bar k, p naught equals h bar k. So all the intuition you have about momentum, you can translate into intuition about the spatial variation of the phase of the wave function. Yeah? Oh, okay, good. Okay, good. So we have a sneaky rotation today. So the information about the momentum can be encoded in the spatial variation of the phase of the wave function. So another way to answer the question then of what is momentum, apart from it's the thing that, so what are ways to answer the question what is momentum, you could ask, well, what is momentum? It's the thing that commutes with p or with x by I h bar. That's one way to answer it. Another way to answer it is to say that translations by L can be expressed in terms of momentum as e to the minus I upon h bar p L. Okay? So these are both ways of describing what the momentum is, but another way of talking about the momentum is the momentum, p, governs the the spatial variation, the x dependence, of the phase of the wave function. Okay. So these are all ways of talking about what the momentum is. So now let's turn this around. Let's ask about the crystal moment. Oh, and one last thing. A last defining property of the momentum, it's a central property from the Schrödinger equation, is that the time variation, the dt of p, is equal to the expectation value of minus d, the potential of x dx, right? Also known as the force. So this is the Ehrenfest theorem statement that the classical equation of motion, p dot is equal to the minus d dx, or minus is equal to force. The Ehrenfest theorem tells us that the classical equations of motion are realized as expectation values. And equivalently, if there's no potential is constant, this tells us that the momentum expectation value is time independent, right? Familiar fact. So these are all true, lovely, and things about the momentum. So let's turn all these facts around into the crystal momentum. So let's talk about crystal momentum, which was the question. What is the question? Crystal momentum. So the crystal momentum is defined from the beginning from the following property. If we have a potential v of x, which is invariant under shifting by one lattice spacing by some L, v of x, then this tells us that the energy operator is invariant if we shift by L, if we translate by L, equals 0. And from this fact, we deduce via block or a la block that the wave functions are really the energy eigenfunctions can be written in the form EQ is equal to E to the I Q x, U of x, or U function. So what is this parameter Q doing? Q is governing the spatial variation of the phase of the wave function. Cool. So in precisely this sense that means that the momentum governs the spatial wave function. Here, in the case of a periodic potential, the crystal momentum Q is governing the spatial variation of the phase of the wave function. Okay. So Q is the thing that governs the phase as a function of x. Okay. Well, what about another fact about the crystal momentum, which you show in your problem set, is that if you impose an external force, dq, dt, another d for q, dt is equal to d dt of the expectation value of h bar q is equal to minus the expectation value of the force I'll just write. Okay. So again, this is a quantity, and this was assuming that we had a sharply peaked wave packet. So this is for a wave packet sharply peaked at q naught. So let me just write this as h bar q naught. So the central value of your wave packet. So this is what you show in the problem set. The central value of your wave packet, peak of your wave packet, varies in time according to the external force. And so in particular, if the force is 0, if we turn no external driving force, your wave packet maintains its crystal momentum. It's time independent. So the crystal momentum is something that's time independent unless an external force is applied, just like the momentum. And it's something that governs the phase of the wave function, just like the momentum. However, it's different in a crucial way. It is not the eigenvalue, p on phi sub eq, is not equal to a constant, p naught, times phi sub eq. Right? Because when we act with p, or we act with the derivative, we pick up the term over here, which gives us a constant, but we also have this overall periodic piece. And its spatial variation is generically non-zero. And if the potential is non-trivial, it's always non-constant. So when the momentum operator hits this guy, it will generically not give us 0. Then we get two terms, and we will not get an eigenvalue equation. So q is not the eigenvalue. H bar q is not the eigenvalue of p. And what's the last important property of q that's different from the momentum? It comes from the commutator, which tells us that the thing that's conserved is the expectation value of TL, is really. And in particular, what this tells us is that the eigenfunction, or the eigenvalue of our wave function under translation by L is a quantity that can be shown simultaneously with the energy. However, the eigenvalue of T sub L on this state is equal to E to the IQ up. Which means that Q is only defined for determining the eigenvalue up to 2 pi over L. If you have Q, which is 0, and you increase it to pi over L, that value pi over L is effectively the same as the value minus pi over L. Okay? Because it leads to the same eigenvalue. But that's really strange, because that means that Q itself is not strictly conserved. It's conserved mod 2 pi over L. When you have momentum conservation, momentum is strictly conserved if there's no force. And even if there is a force, it's increasing controlled by the force. As you turn on the force, it just constantly increases. But the crystal momentum, that's not the case. You turn on a force, it increases according to the conservation law. But it's not increasing constantly, periodically. It's periodically fine. So it increases and it ends up at a smaller value. It increases and ends up at a smaller value. Okay. So it carries many of the same properties. It governs the phase. It's time independent unless there's an external force applied. It's the eigenvalue, controls the eigenvalue of an operator that commutes with the energy when you have periodic potential. In the same way that the momentum commutes with the energy when you have no external force, when you have constant potential. Did that help? Good. Okay. So developing an intuition for the crystal momentum, I think, is best done by just playing with examples. And you'll do that more in the course on solids, which I encourage you all to take because it's really beautiful stuff. But for our purposes, this is going to be the full set of ideas we'll need for beautiful. But yeah. So good. So thank you. So This involves a slight subtlety, which I've been glossing over in the entire story here, which is the following. So, is u of x a real function? Well, so when we started out asking what are the eigenfunctions of the translate by L operator, all we showed was that, and I'm going to do this on a report just to make it clear. Tell me if this turns off because okay, cool. So when we started with translate by L and we constructed the eigenfunctions, we said that translate by L q phi, I'll just say phi sub q, is equal to some phase, and this is unitary, so the time value must be an actual phase, it would be I alpha of phi sub q. And let's just suppose that this is true, that phi sub q times e to the minus I q up equals q. So I'm just going to use this to define a new function u sub q, or just u, well, u sub q, fine, x. So this defines a new function u sub q. I take an eigenfunction and multiply by some phase. Sorry, I mean e minus I qx. Okay. If we choose ql to be equal to alpha, then acting on u sub q by translate by L on u sub q of x is equal to, well, if we act on phi sub q translate by L, what happens to phi sub q? We pick up a phase e to the alpha. What happens to e minus I qx? X goes to x plus L. We pick up a phase e to the minus I ql. So if ql is equal to alpha, those two phases cancel, and we just get u back, u sub q of x. But translate by L, u sub q by definition is equal to u sub q of x plus L. So what we've determined is that if we pick ql is equal to alpha, then phi sub q, if I can now be labeled by its eigenvalue q, can be written in the form e to the I q x, u sub q of x, where this is periodic. Everybody agree with that? Okay, so that's step one. Step two is to say, well, look, since the eigenvalue of this guy under T sub L, e to the I q alpha, e to the I alpha is equal to e to the I q L. Since this is periodic under shifts of q by 2 pi upon L, I can just choose to define q up to 2 pi over L. So q, I will take the equivalent to 2 plus 2 pi over L. And the reason I'm going to do that is because it gives the same eigenvalue. If I want to label things by eigenvalues, it's sort of redundant to give multiple values to the same eigenvalue. Now there's a subtlety here, though. And the subtlety here is this. Suppose we have a free particle. Does a free particle respect translation by L? So if we have a free particle with potential 0, that constant function is also periodic under shifts by L, right? Because it's just 0. So it's stupidly periodic, but it's periodic nonetheless. So now I'm going to ask the following question. What are the common eigenfunctions of the energy and translate by L for the free particle? We did this last time. So the common eigenfunctions of translate by L and the energy are the wave functions phi sub q, comma d, are equal to e to the I qx times some function u of x on general grounds. What we know what these eigenfunctions are, they're just e to the I kx, where k squared upon 2m is equal to e. H bar squared k squared upon 2m is equal to e. So we know that these are the correct eigenfunctions, but we're writing them in the form e to the I qx u. Now you say that's fine, there's nothing wrong with this. We just say u is constant and q is equal to k. Right? Then these functions are of this form, but they're of this form with e to the I qx being e to the I kx and u of x being constant. Right? There's nothing wrong with that. Does everyone agree? Perfectly consistent. However, I thought we said that q is periodic by 2 pi. If q is periodic by 2 pi, then that would seem to imply that k is periodic by 2 pi. We know that's not true because any k is allowed for free particles. So if we want to think about q as periodic by 2 pi upon L, then we cannot require that u is real. Because it must be the phase that makes it something must be. So I can always write this as e to the I qx, where q is less than 2 pi upon L. Or sorry, q is between 2 pi upon L and minus pi upon L. Right? So that it's defined only if it's periodic thing. But times some additional phase, e to the I k minus q x. So this is trivially equal to e to the I qx. Right? But now u is not a real function. On the other hand, if we hadn't imposed the requirement that q is periodic, we wouldn't have needed to make u real. We could have just taken q to be equal to k for any value k, and then u would be constant, u would be real. So this is important for answering the excellent question that our fearless recitation instructor provoked me to answer, which is that, so we'll come back to the question in just a second, but I want to emphasize this, that if we're going to take q to be not periodic, or sorry, if we're going to take q to be defined only up to shifts by 2 pi over L, it's important that we allow u to be not real. It must be able to be an overall phase. But if we want u to be always real, we can do that, we just can't impose this periodicity. Different values of q mean different wave functions. And this is really what's going on when you see those plots. Sometimes you see the plots as parabolas, the bands are represented by parabolas with wiggles, and sometimes they're folded up. And that's the difference. The difference is that when you fold them up, you're imposing this periodicity, and you're labeling the eigenfunctions by q and the overall amount of the number of k effectively of k phases that you're subtracting off. Yeah. Yeah. How to say it's exactly akin to a choice of variables in describing the position of this particle. Should we use Cartesian coordinates or should we use circle coordinates? Well, it can't possibly matter, and so you better make sure in any description of your system that changing your coordinates doesn't change your results. And here, that's exactly what's going on. If we want to define our variable to be periodic by 2 pi upon L, well, okay, then u can't be real. Or we can take q to be not periodic by 2 pi L and impose that u is real. It's just a choice of variables, but it can't possibly give different answers. But the point is, this is a subtle little distinction that we gloss over, and it's glossed over in almost every book on different mechanics that even covers periodic potentials. It can be very confusing. Anyway, the reason that I had to go through all this is that in order to answer the very, very good question that Professor Adams posed, I'm going to need to deal with this fact. So for the moment, let's work with U real and Q in Q an unconstrained real number. Okay, so not periodic. Pull that for the moment. Okay. So if we do that, then notice the following nice property of our wave function. Our wave function phi of Q is equal to e at ux times U of Q or ux, which is real. So when we construct the current, remember that J boils down to the imaginary part, h bar over 2m, I, h bar over m times the imaginary part of psi complex conjugate derivative with respect to x, which is the current in the x direction of psi. And we need this to be imaginary, or we will get no current. You show this in a problem set. If you have a pure real wave function, for example, a single real exponential that's decaying, right, as on the wrong side of the barrier, then you get no current. Nothing flows. And that makes sense. It's exponentially decaying. I think it's cross. So we need the wave function to be real. So if q were 0, we would get 0. And what you can immediately compute from this, is that, well, the derivative, if the derivative doesn't hit e to the iqx, if it hits u, then the phase e to the iqx cancels. And so the contribution from that term vanishes. So the only term that's going to contribute in here is when the derivative hits the e to the iqx. So then this is going to be equal to h bar. Whoops. Oh, and did I get my... okay, good. H bar q. And we want the imaginary part, so that's going to be e to the I over m. And then we're left with u squared of x. Okay? So this is the current. But we have to take advantage, in order for this to be sort of clean, we have to take advantage of u being real. Remember that? So there's one last twist on this, which is that if I have q, this is a side note, going back up here to this logic. If I have q, and I can always write it as some q naught plus n pi over l. Okay? And so now what I want to do is I want to take sort of a hybrid of these two pictures, and I want to say phi, so q, is going to be equal to e to the I q naught x, where this is the value that's periodic by 2 pi, e to the I n pi over l x u. Okay. And so now really what I'm doing here is I'm labeling q not by a single number, or I'm labeling my wave function not by a single number q, but by q naught and an integer n, comma n. So q naught and n. And so now q naught is periodic. It's defined after shifts by 2 pi. N is an additional integer, and what it's telling you is how many times you have to shift back to get into that fundamental zone between pi and minus pi. And this fits nicely into the story because now all we're going to get here is q, which is q naught plus n pi. So the current depends on both the part defined mod 2 pi over l and the integer, which tells you how many factors of 2 pi over l you have to subtract off to get into that fundamental domain. Well, let's think back to our band structure. So what is this n quantity? Let's think back to our band structure. In our band structure, we have something that looks like this. And here's the value of q. But am I applying q? No, I'm applying here q naught. I'm applying the part that's periodically defined up to 2 pi over l. So this is pi over l, this is minus 2 pi over l. Okay. And what we see is that there isn't a single energy, right, because this is the energy of the vertical direction for these n pictures, there isn't a single energy for a given value of q. In fact, the set of energy eigenvalues, or the set of allowed states or energy eigenvalues for an allowed value of q, let's say this particular value of q naught, how many of them are there? Well, there are as many as there are integers. 1, 2, 3, 4 count. So to specify a state, I don't just have to specify q naught, I also have to specify n, which one of these guys I'm hitting. And when you unfold this into the macro picture, remember where these came from. These curves came from shifting over. And the higher up you go, the more you have to shift over. And that's exactly the energy piece, n pi over l. And so we can write the current now in terms of h bar q naught upon m, u squared, h bar q naught upon m, plus n pi h bar upon m, u squared of x. So we get a contribution from the crystal momentum and from which band we're in. Okay? So it's sort of an elaborate story to answer the phase question. But yeah. Good. So here we have psi. So psi. Oh, sorry. I should have done this for phi. I meant this wave function, right? Okay. So this is phi. This is phi. Q. Q. So from here, we're getting the imaginary part. The imaginary part of this wave function, which is either minus iqx u of x, derivative of e to the iqx u of x. Now the derivative is when the derivative hits the e to the iq. X pulls out a factor by q, and there's two factors cancel from these guys. You just put u of x here and u of x here. Oh, so this is the potential. Good, that's the point. So this isn't the potential. So in the state of that, when we have this translation by x, so this is just some function. It has nothing to do with potential. It's defined in terms of the wave function, the eigenfunction of translate by L. So if we know, so the logic here goes, if we know we have an eigenfunction of translate by L, then I construct a new function u, nothing to do with potential, just a new function, which is e to the minus iqx times it. You can't stop me. You hand me a function, I will hand you a different function. And then we pick q felicitously, so to show that u is periodic. So u is just some periodic function which is defined from the wave function, from the energy, from the eigenfunction of DL. Did that answer your question? Okay. So here it just came from the fact that u is, phi is e to the iqx u, and then there's a factor u for each of these. Other questions? Yeah.
What is that you should actually look like when you unfold it?
Awesome. So this picture when it's unfolded, first off, you know what it is for a free particle. So we want the energy as a function of q. So what is it for free particle? Parabola. Yeah, exactly. And now let's add in let's make this is a function of q, not q naught. So here's pi over L, here's 2 pi over L, here's 3 pi over L. And I need to do this carefully because it's incredibly difficult to get this straight. Okay, let's call it. Okay. My artistic skills are not exactly the thing of legend. Okay, so here's the problem that would have been if we had not turned on a periodic potential. As we turn on the periodic potential, we know that the energies, the energy is changed. And so in the first band, it's easy to see because from minus pi over L is pi over L. We don't have to do anything. Pi over L. So it looks exactly the same as the lowest band here. So in particular, okay. So what about the second band? Well, what I want to know what's the other allowed energy at say plus pi over L. So plus pi over L is going to be something greater than this value. But plus pi over L, we already know the answer from the diagram because plus pi over L is the same as minus pi over L. So what's the value over here? Well, the value over there for the second band is slightly above, and then it increases and decreases. So it's slightly above, and then it increases. Shift by pi over L. Oops, did I shift by pi over L? This is this guy. That's 1, 2, 2. Yes, I did. Good. Okay, and it goes the other way. So just noting that it goes the other way from the top. I have a hard time drawing these things. Okay. So for every value of q, there's allowed energy. But it's different than it would have been for the free particle. And then we do the same thing for the next state, and it looks like this. So now imagine what happened. We take this and we fold it over. 1, 2. What we get is a band that should look like this. That's what the second band should look like. Okay. And indeed, when we put it in the fundamental domain, this is what we get. This is what the first band and the second band together look like. And then the third band, we'll move this over once and then twice. It's going to look like this. And this guy, move it over once, twice. Looks like, oops. Good. Yeah.
Respect to K instead. That just get around with dotted lines then. So why do we not? Really?
If we wanted plus RC.
E as a function of K instead of Q.
Oh yeah, E as a function of K is always going to look like that, but K is not a local. So what is K? K is just defined as h bar squared, k squared upon 2m is equal to E. So this doesn't tell you anything, right? Because any allowed K, okay, sure, any allowed K is some value of E. This doesn't tell you which E values of E are allowed. Only some values of E are allowed, right? There are no values of E. There are no energy eigenstates with energy in between here and here, right? And so that tells you there are no allowed Ks because K is just defined. It's just completely defined by E. So this doesn't tell you anything about which states are allowed. It just tells you that given an E, there's some quantity of defined K. This is a definition of K in terms of E. What this diagram is telling you is which E's are allowed. Sorry, say again. An L? Yes, that should be it. Yes. Let's see. What's Q? Sorry. Q. Yes. Yeah, you're absolutely right. Over L. Thank you. Excellent. That's exactly right. Yeah. Oh man, I made a dimensional mistake. Thank you. Jesus. Okay. Good. Yeah.
If you re-explain sort of how imperfections in the lattice actually contribute to the conduction problem.
Yeah, I'm going to do that. So that's the next question. The question is, could you explain again how imperfections in the lattice lead to actual conduction? As we talked about last time, when you have a perfect lattice, there is actually no current flowing in response to an applied electromagnetic field. If you put on a capacitor plate across the perfect lattice, you don't get any current. The charged particle in your lattice just oscillates back and forth in a block oscillation, running up the band and down the band, up the band and down the band. So how does that? So let me slightly change your question and turn it into two other questions. The first question is, given that that's obviously not what happens in real materials, why don't we just give up on quantum mechanics and say it totally failed? Right? And so this is a totally reasonable question, and I want to emphasize something important to you, which is the following. That model led to a prediction, which is that if you put a capacitor plate across a perfect crystal, then you would get no current flowing across. You would just see that the electron wave packets oscillate. The block oscillations as discussed last time. And that is manifesting what happens with copper. But the experimentalist comes back and says, look, dude, that is a ridiculous model because the copper isn't in fact perfect. It's messy. So how do you test the model? Well, there are two ways to test to deal with the situation. One is to improve the model, to incorporate properties that copper actually has, and see if you can actually get the same conductivity that you see. But the other is you could improve the material instead of improving the theory. So can we actually build a perfect crystal? So it's actually something that I'm doing research on right now, not on the building side, but on the theory side, because I'm theorists, you should not be in lab. But I collaborate with experimentalists, so they're nice people. So very good physicists. So here's something you can do. You can build a system that has exactly a periodic potential. It turns out it's very difficult to do this with quantum systems, but what you can do is you can do it with lattices not of atoms, but lattices of dielectric. So the equation, here's a cool fact, the equation for light going through a dielectric, where the dielectric has different constant, like waveguides, you've got glass, you've got air, you've got glass, you've got air. That equation can be put in exactly the same form as a Schrödinger equation for the time evolution of a wave function. They're both waves, and so it's not so surprising that these two wave equations are related to each other in a nice way. Meanwhile, the index of the dielectric turns into the potential for the quantum mechanical problem. So if you have a periodic potential, what do you want? You want a periodic dielectric constant. Yeah? And so you can build a system which incredibly cleanly has a periodic dielectric constant and no disorder. And then you can put light into the system, and you can ask, what happens to this system? So here's the idea. I take a a system which is periodic. I'm going to draw the potential here. So I'm going to draw the dielectric constant. So small, large, small, large, small, large, small, large, etc. Okay. But instead of having a one-dimensional lattice, I'm going to make it a two-dimensional lattice. So now basically I've got a set of waveguides, or let me draw this slightly differently. Okay. So does everyone get the picture here? So literally what you have glass with a different index, glass with a different index. You think of this as a line of glass fibers, of optical fibers. And you shine your light that's reasonably well localized in both position and in phase variation, or crystal line, because you can control the phase of the light. So you send this wave packet and you ask what happens. Well, not a whole lot happens. It's a wave packet. It's going through a waveguide, but we haven't implemented an electric field. To implement an electric field, you need a potential to be constantly varying. So let's add a layer ramp into the potential. Instead of making it just perfectly periodic, let's make the index ramp just a little bit. And this experiment has been done. And this experiment, so as the wave packet moves along, what's discovered is that the position, if I draw the x as a function of t, so now the role of t is being played by the distance it's moved along the waveguide. What you find is it does this. And you get its beautiful block oscillations. And this has been probed in a very small number of real, honest quantum mechanical systems. The most elegant experiment that I know of was done by Wolfgang Ketterle, who's here at MIT, and he got 3 data points because it was preposterously difficult to declare victory. So I talked to him about this in the hallway one day. He said, yes, this was ridiculous, but we got 3 data points. We got small, we got large. Victory. We declared victory. But it really needs to be done well. So one of the interesting questions in this part of the field right now is we know that it's true, but we want to see it. We want to feel it. So various people around the world are working on making a truly beautiful demonstration of this bit of physics. Yeah?
Is this is it a
it's totally impractical because any interference is just going to kill you. Yeah, unfortunately. So you have to work ridiculously hard to make systems clean. So the question is really a question about quantum computation, which we'll come to next week. But the basic question is how robust is this? And the answer is it's not robust at all. But we can tell because everything in the real world has enough impurity that it can nuts. Organisms, yeah.
It's sort of like the larger role in sort of like the perfection of a lattice, like temperature or impurity.
That's a very good question. So the question is, what's the most important property? What's the most important disordering property that leads to conduction? And the there are impurities in the lattice, there are ecothermic effects, which are more complicated, and that's actually, it depends on the situation, it depends on the system. And exactly how it depends on is something that is not very research. Now, there are many ways to probe this physics. We know that these block oscillations are true. We see them in all sorts of different systems that are analogous. So there's lots of reasons this is an ambiguous bit of physics. But I just want to turn out these friendly field key part. The reason I bring all this up is that phone, our model interpretation that disagrees explicitly with the conductivity property of copper and other materials. So don't throw away the model. Observe that you've modeled the wrong system. If you find a system that fits your, that shares the assumptions of your model, that's when you ask it to work, and it works like a champ. Okay, so now let's talk about real materials. This is going to close up our discussion of bands and solids. This is actually what I wanted to get to at the beginning of the lecture. That's okay. There are lots of questions, and they were good questions. So this is going to be extremely brief. But I want to ask you the following question: what happens in the following 3 systems? So first, imagine we take a system with built out of single wells, which have some set of energy eigenstates. Okay, and then we build a periodic array out of them. Okay, what do we expect? Let me draw this bigger. Bounce. What do we expect to see when we build a lattice? We expect that these states are going to spread out into bands of finite width. Yeah, and let's just talk about the 1D potential. So what we'll find is that this band turns into, this single state turns into a band of a lot of energy eigenstates. Okay. So this is now a plot of the energy. And similarly, this state is going to lead to another band with some width. And this state is going to lead to another band, which is even wider. Ever cool now? Quick question: in 1D, did these bands ever overlap? No, by the note here, right? Okay. Now let's take a single electron and let's put in. Let's take a single electron. Let's put it in the system. What will happen? Well, if we put it in the system, what state will this single electron fall into? Yeah, one of the bands. Which state? Yeah, if you kick the system around, you let it relax a little bit, it's going to fall down into the ground state. You have to couple it to something else, like hydrogen has to be coupled to electromagnetic field to decay, but couple it, kick it, and let it decay. It'll settle down to its ground state. So you get an electron down here in the ground state. And looking back at that band, we know that the band for that ground state looks like this. This guy. So here it is. There's our electron sitting in the lowest energy eigenstate. Is it moving? Well, it's in a stationary state. Is the expectation value of the position changing in time? No, the expectation values don't change in time in the stationary state. That's part of what it is to be a stationary state, to be an energy eigenstate. Okay, here, it's not moving. Now, in order to make it move, what do you have to do? What kind of state corresponds to the position changing in time? Yeah, superposition, right? From superposition, we'll get interference terms. So if we put it in a superposition of, say, this state and this state, which corresponds to different energies, if we put it in the superposition of these guys, then it's meaningfully moving. Yeah? It has a meaningful, well-defined time variation of its position expectation value. So in order to induce a current, a current of the system where the electron wave packet carries a little bit of momentum that's changing in time its position, what do I have to do to the electron in the ground state? I have to excite it so that it's in superposition of the ground state and the excited subexcited state, or more generally, into a superposition of other states. Yes? In order to induce a current, I must put the electron into a higher energy state and into a superposition of higher energy states. Ever done that? Here's why this is so important. Imagine each one of these wells is actually not some square well, but it's an atom. Okay? And let's say the atom is hydrogen, just for, this doesn't actually happen, but just imagine. So anything what it means is it has the ion, the nucleus is charged +1. And so in order for the system to be neutral, I must have one electron for every well. So if I have n wells, I must have n electrons in the system. Ever agree with that? In order to be neutral, otherwise the thing's charged and all sorts of, electrons will get ripped off of nearby cat. So we must have an electron per well. How many states are in this band? For n wells. N, right? And okay, so if I put in the n electrons I need to neutralize the system, where do those n electrons go? Yeah, they fill up the first band. And if we let the system relax with lowest energy configuration, every state in this lowest band will be filled, and none of these states will be filled. Ever done that? So here's my question. When I've got that ground state configuration of this lattice of atoms with one electron per well in these distributed waveforms, filling out these bands, is anything moving? Oh, you guys are so quiet. Is anything moving? The system is in an energy hiding state. In particular, it's in a completely anti-symmetrized configuration because they're identical fermions. So nothing is moving. If we want to induce a current, what do we have to do? Yeah, we have to put them in a superposition. But where's the next allowed energy hiding state? Next band. So in the next band, it's the next allowed energy hiding state. So the configuration we have now is that these guys are all filled. These guys are all empty. But in order to take an electron from here and put it in this excited state, we have to put in a minimum amount of energy, which is the gap between those two bands.
So let me just write this down.
So now think about it this way. Suppose I take light and I send my light at this crystal. In order for the light to scatter off the crystal, you must have electrons in superposition states so that they can have a dipole and absorb and radiate that energy. Yeah? But in order for that to happen, the light has to excite an electron across the gap. It has to give it this macroscopic amount of energy. Well, that macroscopic is large. It's not infinitesimally small. That means that there's a minimum amount of energy that that incident light must have in order to excite the electron in the first place. So very long. Wavelength light will never do that. Light of long wavelength will not have enough energy to excite an electron across this gap into the next band to allow there to be a current, which would oppose the electric field. So the only way for light to scatter off of this crystal is if the energy, h bar omega, of the light is greater than or equal to, well, let's just say greater than approximately, the band gap delta E. That cool? We just discovered something. Crystals are transparent unless you look at sufficiently high frequencies. That's cool, right? A crystal is transparent unless you look at sufficiently high frequencies. If you look at low frequencies, your crystal should be transparent. Well, that's really interesting. In particular, we immediately learned something cool about two different materials. Consider diamond and copper. These are both crystals. They're solids made out of a regular array, perhaps not perfect, but extraordinarily good, regular array of atoms of the same kind. Array of particular structure, diamond, I think, space cubic. I don't remember. I really should know. Anyway, copper, it's the labs. So, that's embarrassing. I really should know that. We have these two materials. Which one has the larger band gap? Diamond, because it's transparent and invisible. So the band gap, delta E, of diamond is much larger than the band gap for copper. But in fact, this is a little more subtle because copper, in fact, doesn't even have a band gap. We made an important assumption here. So I want to think about, we're going to come back to copper in a second, but I want to point out the nice thing here, which is that diamond has to have a band gap. It's transparent. It must have a band gap. It must be such that when you fill up all the energies, all the electrons you need for it to be neutral, there's a gap to the next energy state, and that gap must be larger than visible wavelengths of light. Yeah, that's cool, and that must be true of all the transparent crystals that you see. Otherwise, they wouldn't be transparent. They would respond by having free electrons that could respond like a metal. Yeah.
So is this the original materials from
Yeah. These copper bears are diamonds conductors? No, they're terrible conductors. In fact, they're preposterously. If you compare the number of, well, okay, I'll get into this later, but yes, that's terrible. That's a slightly more complicated story, which we can come back to. Hold on to that. I'm going to answer today. Ask me after, and I'll start because it's a little more. What? Really?
Yeah.
Wow. Well, MIT. Okay. It's all about the intellect. Everything else has to be. Okay, so this is pretty good, but here's the thing. In one-dimensional crystals, the only thing that can happen is, look, if you have each band comes from a lab energy state, and each energy state, each well comes with 1 electron or 2 electrons or 3 electrons, you will always have filled bands in the gap and then filled bands in the gap. So we agree with that? You can't have a partially filled band if each band comes from the bound state in a single well, and each well comes with an integer number of electrons. You're just stuck. Yeah. So I'm lying about spin, but spin in one dimension is a little. I'm lying about spin. Okay. But do you really want to get into spin? Man, okay. So if we include spin and we have splitting, then it becomes a more subtle story. If we include spin, then there are 2 states for every allowed energetic state of the potentials. However, there are generically going to be interactions between the. There are generically going to be magnetic interactions which split the energy of those 2 spin states. Electrons spin out, electrons spin down, generically have different energies. Now, in 3D, this isn't such a big deal because the splittings are tiny, and so the states can sort of overlap. But in 1D, they can't. So, I mean, that's also not exactly true, but it depends on exactly the details. So it depends on the details of the system. That's what I want to get to. So let's let me talk about the same phenomena in an easier context where we don't have to worry about spin, which we haven't discussed in detail in class, which is in 3 dimensions, where the story changes in a dramatic way. Yeah. Yeah. Oh, it's not. No, generically, it's not. It will depend. Yeah, exactly. I'm just saying it happens to be the salient one. The salient, yeah. That's exactly right. No, the gaps are not the same. They do not remain constant. That's right. Okay, so let's talk more about this system. Let's talk about the 3 dimensions. So in 3 dimensions, you guys did an interesting thing when you studied you didn't know that this was about the structure of solids, but it really was. When you studied the rigid rotor, and when you studied the rigid rotor, you found you had energy eigenstates, and they were degenerate with degeneracy 2L, or 2L plus 1, right? The various different LZ eigenstates. Yeah. And then we turned on an interaction, which was the energy cost, the energy penalty for having angular momentum in the z direction, which added an LZ term to the energy. And what we found is that as a function of the coefficient, which I think we called epsilon, of that perturbation of the energy, so that the energy was equal to L squared over 2I plus epsilon LZ. What we found is that these guys split, this remain constant, and this split goes into, so this is, L equals 1, so the L equals 0, so this is 1, this is 3, this is 5. So the L equals 0 state, nothing happens. The L equals 1, there's one that changes, one that doesn't. And then this guy has 5, 1, 2, 3, 4, 5. Okay, and what we found here is that these guys could cross. States from different multiplets with different values of L had energies that could cross as a function of the strength of the deformation of your system, right? With the deformation of the sphere, you stick at your own. So it's no longer symmetric top. So here we can have states crossing. There's no node theorem in 3 dimensions. So as a consequence, when you have a 3-dimensional material built out of atoms, so here's my sort of pictorial description of a 3-dimensional system built out of atoms. You have potential, 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 potential well. Now, if the energy in one particular potential well is like this, and like this, and like this, then when we add in a lattice, we get bands again. The structure is a little more intricate because it depends on the momentum, but these bands now can overlap. Okay. Ever see that? Because there's nothing preventing states from different multiplets from having the same energy in 3 dimensions. There's no node theorem that tells you have to keep the ordering constant as you turn on the potential. Now we turn on the multiple part potential, and they can interact. They can overlap. As a consequence, when we fill up, let's say we have 2 electrons per potential or per well. When we fill those first 2 bands, well, there is the first. The first band is now filled. The second band and part of the third band, and most of the second band are going to be filled, but part of the second band is now available, and much of the third band is now available. We filled in 2 electrons, but we haven't filled up this band because it's really 2 bands jammed together, or really bands from 2 different orbitals jammed together. They happen to overlap. One second. So as a consequence here, if this is the energy of the last electron that you put in, how much energy do you have to give the system? Do you have to add the system to excite the energy, or to excite the electrons into excited states, and if you go into superpositions so that the electrons can move? Yeah, a preposterously small amount. An amount that goes like 1 number of particles. Right? So in the continuum limit, it's 0. There's arbitrarily nearby energy. So how much energy does it take to excite an electron and cause a current that opposes the induced electric field? Nothing. Any electric field that you send in will be opposed by an induced current. So this behaves like a classical conductor. You turn on an electric field, and the charges will flow to oppose that externally imposed electric field. You get charges then building up on the walls of your capacitor plates. Cool? So this is a system where we have a conductor. Because there's an unfilled band. And back here, we had an insulator. Because we had filled bands separated by gap. The gap between the filled band and the next available band. Okay. This is actually called a band insulator, so other ways of being an insulator. But... So from this, just from the basic quantum mechanics of a particle and periodic potential, we now understand why some crystals are transparent, why some materials conduct, why the materials that are transparent are also insulators, and the things that conduct are not transparent, right, generally. Yeah? Excellent question. So what's so special about diamond and different from copper? And so the answer goes like this. So what determines the exact band structure for a 1D periodic potential? Two properties. One was L, the periodicity, and that came in the QL and KL, right? And the second is the detailed shape of the potential. Now, in 3 dimensions, the story's going to be a little more complicated. In 3 dimensions, the things that are going to determine the potential are not just the distance between atoms, but you have 3-dimensional lattice. And the 3-dimensional lattice could have different shapes. It could be cubic, it could be hexagonal, it could be complicated in all sorts of different ways, right? It could be bands, it could be rhomboidal, and it could have all sorts of different crystallographic structures. So that's going to go into it in the same way that L went into it, which is the only primary in 1 dimension, in the same way that L goes into it. So the crystal structure, the shape of the lattice is going to be different. Secondly, the structure of the orbitals is different. Different atoms are different wells, so they'll give you different band structure. So different materials, for example, diamond versus copper, are going to give you different bands of loud energies because the potential is different, right? It has different shape. And so when you solve the problem for the energy eigenvalues as a function of now the 3 different components of the crystal momentum, you just get a different set of equations. And working those out is not terribly hard, but it does, it's a computation that must be done, and it's not trivial. And so one of the sort of, I don't know if I'd say exciting, but one of the things that one does when one takes a course in solids is you go through a bunch of materials and you understand the relationship between the potential, the atomic orbital structure of the individual atom, the crystal structure, and the resulting band structure. And there's some sort of nice mnemonics, and then there's simple calculations that you do get the answer. You will almost always find overlapping bands in 3 dimensions sufficient high energy. Yeah, I can't off the top of my head give you a theorem about that, but yeah, it's generic. Yeah.
Is analog to a conductor in 1 dimension? If you have these like non-zero band gaps.
Yeah, and this is why Matt was barking at me. So the answer to that is yeah, there are analyses, but what would we need? What we need is we need one of 2 things. We need either the band gap coincidentally is ridiculously small. What's a good example of that? A free particle. In the case of a free particle, these band gaps go to 0, right? And so that's a conductor. Right? It's just an electron. Right? Conducts, right? Okay, so that can certainly happen, but that's sort of stupid. I mean, it's not totally stupid, but it's sort of stupid. But a better answer would be, well, can you have a system where there are bands, but you didn't have 1 electron per potential well? And yeah, you can orchestrate that in lots of ways. Now, it involves orchestration. So it's not the generic system that we were talking about here. But you can orchestrate. So spin is a useful thing that gives you an extra handle. If you have twice as many states per well, then you can have half a band filled. Right? So that's one way to do it. But then it becomes dependent on details of the system, which is what I didn't want to get into. But yeah, you can orchestrate this. It's just not a generic thing from what we've done. It's really not for spinless systems. On the other hand, accidental small gaps, easy. That happens. That certainly happens. So that brings me to the last thing we're going to talk about before getting to entanglement, which is accidental small gaps. So what happens to a system, so there are some systems that are neither conductors nor insulators. They are reasonably good conductors and reasonably bad insulators, but they're not perfect.
I shouldn't do the other way for follow my convention. Let's just remind ourselves what the insulator is. And
These materials are called semiconductors. I want to talk about why they're called semiconductors and what that means. So let's give you a very brief. We're going to get into it. So consider a system exactly using the same logic we've used so far. We have the following problem. We have two bands, and one band is filled. You can have the right number of charged particles. One band is filled, and this band is empty, but the gap is tiny. Okay, delta E is very small. Now, delta E has dimensions as you carry. So when I say small, that doesn't mean it immediately small. So what is the anything that equals an energy scale for a really material? Well, the temperature. If you have a hot piece of copper, then the lattice is wiggling around, and every once in a while an ion can hit one of the electrons and excite it, give it some momentum, and so there's an available reservoir of energy for exciting individual electrons. If you have it really hot, what happens? Every once in a while an electron will get nailed by a little thermal fluctuation system and get excited above the gap. And now it's generically, it's going to be in a superposition state of one of these excited states, so it's in general going to be moving, it can radiate, it will eventually fall back down. But you're constantly being buffeted, the sea of electrons is constantly being buffeted by this thermal fluctuation. And as a result, you constantly have electrons being excited up, cruising around, falling back down, so you end up with some population of electrons. And they can ask, and both can ask, although not quite this language, how likely are you to get an electron up here? How likely is an electron to be excited up thermally? And those of you taking 8044, I know the answer to this. The probability goes as E to the minus delta E over kt. So let's think about where this is the Boltzmann constant. So what does this mean? At very low temperatures, if the gap isn't zero, then this is zero. It doesn't happen. But at large temperatures, the denominator here is large. If the temperature is large compared to the width of the gap, then this is a small number, and E to the minus is a small number. That's close to 1. So at high temperature, you're very likely to excite electrons up here. And now if you have electrons up here, you have a bunch of available states down here, also known as holes, and you have a bunch of available electrons up here with lots of available states. So at high temperature, a material with a small gap, or at least at temperatures high compared to the size of the gap, is basically a conductor. And at low temperatures, it's basically an insulator. This is called a semiconductor. And there are notes on the Stellar webpage that discuss in a little more detail what I just went through and show you how you build a transistor out of a semiconductor. And the important bit of physics is just this. Okay. So that finishes us up for the band gap systems for periodic potentials. We've done something kind of cool. We've explained why diamonds are transparent. We've explained why they don't conduct. We've explained why copper does, and it's opaque. And that's pretty good for 15 minutes of work. You know, it's not bad. But along the way, we also talk about the analogous system of photons, what are called photonic crystals, systems of periodic arrays of dielectrics, like waveguides. And those have the same structure. They have bands of allowed energy and gaps of disallowed energies where no waves propagate through. So you might think that's a little bit of a ridiculous example. So just to close this off, you've all seen a good example of a photonic crystal flying past you. You know that highly reflective, at very specific frequency structure on the surface of a butterfly wing that makes it shiny and blue? It looks metallic. It looks like it's a crystal reflecting at a specific frequency, at some sharp blue. And the reason is, it's a photonic crystal. It is exactly this form. If you look at it under a microscope, you see little rays of protein, which have different dielectric than air. And they form exact crystals, or not exact, but very good crystals, that reflect at very specific wavelengths. And as a consequence, they have a metallic sheen. So why would a butterfly put a photonic crystal on its surface? Well, it's extremely light, it's fairly rigid, it looks shiny and metallic without actually being shiny and metallic, and it's not a pigment, so it doesn't absorb light and decay over time. It's like the best thing you could ever do if you wanted to be a shiny, fluttery, flying thing. So that's what, anyway, so there's an incredible amount of physics in the story of the band gaps, and consider this an introduction to the topic. Okay, so that's it for band gaps, and I want to move on to the remainder, the last topic of our course, which is going to be entanglement quantum computation. And here, I need to give you one quick observation, and then move on to the punchline of today. The little quick observation is this. We talked about identical particles before, and we talked about identical particles in funny states. So for example, if I had two particles described by a wave function, where the first particle would be in the state A, and the second particle is in the state B. And I can build this particular wave function for the first particle being state A and the second particle in state B in the following way. So let's say position A and position B. I could take a single particle wave function chi of A, and the single particle wave functions phi of B. And we've talked about what this tells us, and you've studied this on your problem set. What this tells you is that the probability that finds a particle at point A is given by chi A squared, and this is normalized, so when we integrate against it, we get 1. And similarly, the probability that we find the second particle at B is this thing norm squared, and it's independent of what A is. But we also studied, and so this was called the distinguishable, we also studied the symmetric configuration, which was equal to chi, over chi, root 2, chi of A, phi B, minus, symmetric, plus chi of B, phi of A. And this tells us something totally awesome. What's the probability that I find the particle that I find the first particle at A? What's the norm squared of chi of A, phi of B? We integrate over all phi of B. This is so there's a factor of 1 out. You either find it chi of A or chi of B. However, if I tell you that I measured the first particle and I find it in the state pi, what can you say about the second particle? It's in the state phi. If you know the first particle is in the state pi, the second particle is in the state phi because we measured it, and it's not in the state. The first particle is not in the state phi. So measuring one particle tells you something about the second particle. And this is deeply disconcerting because I could have taken these particles, put them in this entangled state, and sent one particle, off to a distant planet, and the second particle to my sister in DC, and my sister measures this second particle and determines what state it's in, and has immediately determined what state the first particle is in over in this distant planet Zorg. Right? So that's deeply disconcerting. And to those of us who have studied quantum mechanics up to this point, which we all in this room have, those of us who have studied quantum mechanics to this level of development and understand that it is a correct description of many experiments, this should be yet another moment of serious discomfort. We've run into a bunch of these over this one. This one should be troubling to you because, look, how can something here dramatically change the state, the configuration, the initial configuration of a particle arbitrarily far away? Isn't that deeply concerning? And if you think about relativity, this should be all the more deeply disconcerting because how does relativistic causality fit into this? So there was a person at roughly this time here, a little earlier, who was troubled by this problem, and his name was Einstein. And so one of the things that's kind of amazing is that he created an experiment. He created a thought experiment, which we're going to study in detail next week, called the EPR experiment. And there's a beautiful historical story about the setting and the meaning and the particular person. And unfortunately, I'm not a historian, so I can't tell you that story. It sure would be nice if we had someone who wrote a biography of Einstein to tell you a little bit about that story. Oh, look, it's Tom Levinson who wrote a biography about Einstein. So Tom is...
Those of you who have taken courses in chess, and I'm sure that's all of you, because of GIRs, no, this is larger than the usual chess class. So I'm very used to microphones, but not in this context. Okay, yeah, it's on. Can you hear me? All right. There are lots of ways to slice the story of Einstein by the time he reaches the EPR experiment, which is Einstein, Podolsky, and Rosen for the three people who actually wrote the paper. Just to dot the I's and cross the T's on the paper itself, Rosen is apparently the person who first came to Einstein. Physicists in Princeton, after Einstein moved to Princeton, Einstein moved to Princeton in 1933. About 3 weeks before, he moved to Princeton in 1933. He left Germany in 1932, December, about 3 weeks before Hitler took power. And he did so with decisiveness and dispatch, and ahead of almost all of his, I think all of his German Jewish physicist colleagues, and those German physicists for whom Hitler regime was unacceptable, which shows that Einstein really was smarter than most of his peers. There's one of the many different ways you can ascertain that. And so he came to Princeton. He actually went to Caltech before he went to Princeton as part of an ongoing visitorship he had there. Came back to Europe, hung with the Queen of Belgium, who was a friend of his, went to England, and then headed across the Atlantic and took up residency in Princeton at the Institute for Advanced Studies, where he stayed for the rest of his life. And over the course of the, it was 33, he died in 55, I think. I should know that. I think that's right. 22 years. He worked with a lot of different, mostly younger physicists, and Podolsky and Rosen were early members of that chain. So Rosen is talking with him someday and starts to frame this experiment. Einstein develops it. The three of them talk about it. They write the paper and they put it out. And I want to share with you actually a really lovely description of the way the problem was represented in a way by this is from a book that I recommend to all of you. It's actually really, it's hard to find. It shows you Jeremy Bernstein, who's a physicist. He's sort of been around, physicist and writer. He's in his 80s now. He lives in Aspen. He worked with CERN for a number of years. He's always been independent. He wrote for the New Yorker. Anyway, so you've all heard of the physicist Bell, I assume? Bell's inequality? Okay. So Bell had a lovely way to describe, I'm trying to find out, I had this marked and I lost my piece of paper. Basically, I've already lost it. That's terrible. So Bell has this wonderful way of describing this problem of entanglement, and it's based on his description of an actual person. I'm going to read you the actual quote. I'm just going to paraphrase it for you. He had a friend named, I think, Berlstein, or at least someone known to him, who had two quirks, an unusual color sense and a taste for mismatched socks. And so Bell used to say, if you saw Berlstein and you could only see one leg, and that sock was pink, you knew to a certainty, that the other sock was not pink. There were, you come up, I think, I'm trying to remember who this is originally attributed to. Same thing, you have a coin and you cut it in half down the so you've got two coin-shaped discs. You cut the disc in half, and you have one side that's the head and the other side that's the tail. And they're separated. They get handed to two different gamblers, and one gambler tries to cheat the gambling establishment by tossing in his half coin, and you see the head. Somebody, someone at some other casino, somebody else is cheating by tossing in the half coin that only has a tail on it. So there are lots of ways to represent this, and many physicists seem very witty indeed. I come up with different little metaphors for it. So Alan just described for you the basic claim in EPR. It's weirdness that you have two particles that are entangled in some way and then go their separate ways, and thus you have, if you have knowledge of what's the state of one, you have certain knowledge of the state of the other, violating relativistic ideas of locality, and just kind of making you queasy if you're sort of approaching it naively. What Einstein, Podolsky, and Rosen argued was actually something a little bit, in fact, the paper comes to an end on that note of queasiness. But what they argued was a little bit more subtle. Because what they said is, okay, you perform this thought experiment, you send the two particles off, you measure the position of one, you know absolutely the position of the other. That has, you conferred, and the paper turns on a discussion of the connection between a measurement and a physical measurement and a property of physical reality. And that definition for what reality is. And that is something whose, if you can perform a measurement, you know that quantity absolutely. I don't have the mathematics to express that properly, but that'll do for the sample weighting experiment. You can then do another experiment and measure a complementary property, and you know that piece of reality. Can't do so on the one hand, quantum mechanics says you can't know these, you can't know physical reality to this level of precision, and on the other hand, the fact that you can do that measurement violates the relativistic picture of reality. So you have what they claimed was a paradox. And this paper was published, and it received a range of reactions from indifference by younger physicists who said, we don't care that it's weird, we're going to keep on doing quantum mechanics and performing experiments and making measurements and to see where this leads us. Remember, this is happening in the mid-30s, 1935? One of these three books will tell me precisely in a moment. The quantum theory, as it turned into quantum mechanics, developed in its first period between 23 and 27, and by 35 you have enormous numbers of productive results and unexpected things, and the prediction of the positron and then its observation, and the theory is enormously, dramatically, excitingly productive. So those who are really heads down doing work are for the most part saying this is fine, we'll get back to it when we're old and retired and bored. But that wasn't the uniform case, and most notably Niels Bohr found this paper really troubling, and spent about 6 weeks apparently discussing this and trying to come up with a response to it. And what he responded was essentially that, in some ways it was the same reaction as his younger colleagues. Get over it. But more precisely, it was, he said, there's no description of reality that excludes measuring apparatus anymore. You can't make statements about physical reality unless you include a description of measuring apparatus. And you said that we can measure this one quantity of precision and know the other thing, and then we can subsequently, in a separate observation, measure a complementary quality and know the other one. You still can't know them at the same time. It's still true that the complementarity, in essence, means that once you know one part of the picture, you know some other part of the picture. And that's just the nature of the quantum world. Einstein had argued that the EPR paradox suggested that quantum mechanics was incomplete, and Bohr essentially responded, in effect, that Einstein's description of quantum mechanical explanation was inadequate. And the important thing to remember, and I want to just spend a couple minutes going back into the prehistory of all this, and then a couple minutes speculating on why Einstein reached the position he did, and what that might tell you about the practice of science as a lived experience as opposed to one reflected in your textbooks. But the thing to remember is that there's nothing logically wrong with the EPR paper, right? It does what it says it does, and there's no overt error in it. And there's nothing wrong with Bohr's response. And in fact, when the experiments, Bell formalized what Bell's inequality really does is it formalizes the two arguments. It says, if Bohr is right, you will observe this in the experiment, and if Einstein is right, you would observe something different. The experiments were done, and I imagine are still being done as sort of demonstrations, and they show that Bohr's interpretation was correct, and that, yes, quantum mechanics produces results that are non-local, just as Alan described to you, and that the world really is as strange as people first glimpsed in 1925, 26, and 47. And the question of whether or not that strangeness is adequately explained, whether or not the explanations that you're going to learn in this class and subsequent ones are, quote, complete or not. And completeness is a very funny, very, very tricky concept. But whether, the question of whether or not, the framework of quantum mechanics is somehow unsatisfactory in any kind of formal technical sense, is one that's at least partly dependent on your scientific temperament, I think. So that's the cartoon version of what happened in 35. Einstein, with his two colleagues, proposes, really you should understand the EPR paper as a description in detail of consequence of quantum theory as it was then expressed, with the conclusion that Einstein reaches the same. No reasonable definition of reality could be expected to permit such a result. So in fact, it's called a paradox, but it's complete. It's a memo to the flying spaghetti monster that the universe shouldn't be this way if in fact experiments turn out to show that it is, and it happened. So the oddity here for a biographer of Einstein, opposed to physicist, is given what you know about Einstein between 1879 when he was born and say 1925 or so, when he completes the last of his really great physics. How could I mean? I actually keep I've been working on Einstein off and on for years. I keep finding out new ways in which he's just inconceivably bright and on target and knows the right problem and insightful. And yet by 1935, 10 years later, he's still a relatively young man. He's in his 50s, which being in my 50s, he's an extremely young man. Just 10 years after doing work that's right on the edge of modern quantum mechanics that is essential to his foundation. That's I'm really sorry. 10 years after that, he's saying no reasonable definition of reality should be permitted to behave this way. Where does that come from? Well, the first thing I want to tell you, again, this is all going to be a really cartoon version because there's not much time to understand. Is Einstein? How much are you aware of Einstein's role in the creation of the quantum theory? A lot, none. Okay. Except, I'm going to make a claim that except for Heisenberg, Schrödinger, maybe Bohr, maybe a couple of others, there's no one more important to quantum theory than Einstein. And you may even argue that from a sort of foundational point of view, that without Einstein, rigorous thinking about quantum mechanics would have taken much, much longer. He's really central to it. Planck in 1900 publishes as an ad hoc solution to the black body problem the first quantum theory. In 1905, Einstein says it's not an ad hoc thing. If you look at the photoelectric effect, is the particular problem he's dealing with explanation. That's really the behavior of the photoelectric effect is really presented as a confirmation of this idea that light is just response with particular kind of behavior. And from 1905 on, he spent probably more time on quantum problems than he did on any other physics problem, something more than on relativity that we spent, enormous energy on special relativity. One of those instances that Einstein, in fact, is that despite the fact that he's seen and appears by 1935 to be this high powered guy, he can't accommodate himself in the world, is an extraordinary capacity to do what the Red Queen did, Nelson Wonderland, and believe two impossible things before breakfast. This is 1905. April, he publishes Quantum Theory of Light. June, he publishes Special Relativity, which treats light as a wave. And makes no mention of his revolutionary, and he called it revolutionary in a private letter in 1905. So he knew what he had in the quantum theory of light. But in special relativity, go read the special relativity paper. It's actually lovely reading, and it doesn't even matter in that direction. This is a heuristic, this is nothing. So he's capable of doing. There's a reason that year's called the Einstein Miracles, the year of miracles, and in part is because Einstein's able to actually really focus on this. And then I realize I'm still over, so there's several steps in Einstein's quantum journey. But what you should take away is that Einstein's ability to deal with the problems of quantum pictures extends when he's the first person to suggest there may be a problem with causality in quantum mechanics. He does this in 1917, 8 years before quantum mechanics is invented. When he starts looking at what the quote classical quantum theory tells you about emission radiation from inside the atom, you realize you can't predict it precisely. The decay has the same problem. He says, well, I don't want to give up causality, but we may have to. So, he's doing this things. So, I see class is over now, 12:30? Okay, sorry. So, just to finish up, the question here is, why does Einstein give up on this? And the answer, I think, is because in addition to his, as he started at the beginning of his career, he says, with the quantum theory of light and with special relativity, ignore your physical pictures, try and look at the phenomena and explain those. And by 1935, that becomes very difficult for him because the phenomenology becomes too strange. One of the things that quantum mechanics does is it takes away the immediate the ability to visualize physical systems. English is my first language sometimes. And that's an aesthetic failure on Einstein's part. He had the intellectual capacity and explicitly said quantum mechanics is a logically consistent theory that incredibly powerfully describes lots of problems. He said that in print. He nominated Schrödinger and Heisenberg for Nobel Prizes twice. He wasn't stupid. He was Albert Einstein. But he was aesthetically incapable of pursuing this new physics in ways that were possible under the research, possibilities of the time. And that is what I would leave you with. Physics is an aesthetic as well as an intellectual pursuit. So thank you all.
All right, let's go on to 23.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Before we get started, let me ask you guys if you have any questions, pragmatic or otherwise, about the course so far. Seriously? To those of you reading newspapers, I encourage you to find a slightly different time to do so. I really encourage you to find a slightly different time to do so. Thanks. So far we've done basic rules of quantum mechanics, we've done solids, we understand a lot about electrons in atoms, the periodic table, and why diamond is transparent. One thing we did along the way is we talked about spin. We found that when we looked at the angular momentum commutation relations, these guys, we found that the commutators are the same. For these commutators, we can get total angular momentum, L plus 1 times h bar squared for L squared, and h bar m for a constant and integer m for angular momentum in a particular direction, which we conventionally call z. But we also found that there were half integer values of the total spin, and of the spin in a particular direction, which, for example, with spin s is 1/2, 3 has, 5 has, etc. And we discovered that writing a wave function on a sphere that interpreted these states as states with definite probability to be at a particular position on a sphere, a function of theta and phi, was inconsistent. It made the wave function, in order for the wave function to satisfy those properties that have those eigenvalues, and particular half-integer eigenvalues, we discovered the wave function had to be doubly valued, and thus it would equal 2 minus itself equal 0. So the rest of today and tomorrow is going to be an exploration of spin, or tomorrow, next lecture, it's going to be an exploration of spin and the consequences of these spin 1/2 states, exactly what they are. We already saw that they're important for understanding the structure of the periodic table, so we know they're there. And they're present from the experiment, the Sturgeon experiment, that we've discussed many times. But before I get on to that, I want to improve on the last experiment we did. So in particular, in this last experiment, we talked about the effective mass of an object interacting with a fluid, or an object interacting with its environment, and why the mass of the object that's moving is not the same as the mass of the object when you put it on a balance, right? And that's this basic idea of renormalization. And we demonstrated that, right? Demonstrated that with a beaker of water. So I had a beaker of water and pulled a ping pong ball of water. We calculated that it should accelerate upward when released at 20 times the acceleration of gravity, depending on the numbers you use, very, very rapidly. And in fact, it went but it wasn't an entirely satisfying experiment. It's very hard to get the time right. And the basic issue there is that the timescales involved were very short. How long did it take for a ping pong ball to drop from here to the surface? Not much time. And to rise through the water, not a whole heck of a lot of time. So I did that experiment. It was sort of comical. But I wanted to improve on it. So over the weekend, I went down to my basement and tweaked the experiment a little bit. And I called up a couple of my friends, and we did an improved version of this experiment. So this is a diver. I think this one is Kathy. Oh, shoot, we need to turn off lights. And oh, sorry. I totally forgot. Close. Good. And, like, you'll never see this if we don't. Okay. Hello. You can do it. Go. Ah, there we go. All right. And we're in the tank at the New England Aquarium, and she's going to perform this experiment for us. And we're going to film it, as you can see, the bubbles moving rather slowly with a high-speed camera, filming at 1,200 frames per second, with which we'll be able to analyze the data that results. The camera costs, as much as my house. So, and it's not mine. But it's important to have friends who trust you. Okay, so here we are. You might notice something in the background. Okay, before we get started, I just want to emphasize that experiments, one should never take casually the dangers of doing an experiment. When you plan an experiment, you must, ahead of time, design the experiment, design the experimental parameters. We design the lighting, we design everything, we set it up, but there are always variables you haven't accounted for. And a truly great experimentalist is one who has taken account of all the variables. And I just want to emphasize that I'm not a great experimentalist. So here, for example, is a moment.
I think they've muted the audio because there's no, they don't have the copyright here.
Just hit the sharks, it just occurred to me. So anyone who wants to take this experimental data, which was, as you can probably guess, filmed for different purposes, I just managed to get the ping pong ball into the tank. Anyone who wants to get this and actually take the data, come to me. I'll give you the raw footage, and you can read off the positions. And hopefully for next lecture, we'll have the actual plot of the acceleration as a function of time. All right. With that said and done. The moral of the story is you have to account for all the variables. The other moral of the story is that you saw this very vividly. In the motion of the ping pong ball up, when it was released, there's that very rapid motion, very rapid moment of acceleration. When it bursts up very, very rapidly, but it quickly slows in its acceleration. Its acceleration slows down. In fact, a slightly funny thing happens. If you look carefully, again, anyone who wants this can get access to the video. What you'll see is that the ping pong ball accelerates, and then it sort of slows down, literally decreases the velocity, accelerates and slows down. So can anyone think what's going on in that situation? Sorry? Can I say that in slightly more words? Yeah, exactly. So what's going on is as this guy starts slowly moving along, it's pulling along more and more water. Each bit of water around it is starting to drag along the layers of water nearby, and it builds up a sheath of water. Now that water starts accelerating. And the ping pong ball, now that it's, and the ping pong ball and the bubble of water that it's dragging along need to come to equilibrium with each other. They need to settle down smoothly to a nice uniform velocity. But it takes a while for that equilibrium to happen. And what actually happens is the ping pong ball dries up, it pulls up the water, which then drags the ping pong ball. So you can see that in the acceleration, which is oscillatory, with a slight little oscillation. So it's a damped, but not over-damped harmonic oscillator motion. Any other questions about the effective mass of an electron solid before we get moving? Yeah. Right. Why it speeds back up is it's sort of like a slingshot. Is this guy gets going a little ahead of the pack of water? The pack of water has an extra driving force on top of the buoyancy. It has the fact that it's a little bit displaced. So it catches up, but it's going a slightly greater velocity than it would be if it were a uniform velocity. So this guy catches up with the ping pong ball. Okay, so this isn't, of course, in fluid mechanics, but stay, because we don't actually need this anymore. Okay, so picking up on spin. So the commutation relations for spin are these. And as we saw last time, we have spin states. We can construct towers of states because from the Sx and Sy, we can build S minus is equal to Sx plus minus Sy. We can build I. Thank you. So we can build towers of states using the raising-lowering operators S plus minus, and those states need to end. They need to terminate. So we find that the spin can have total angular momentum of S squared, h bar squared, L plus 1, and S in some particular direction, if we can also call T, is h bar m, where L is an integer, or sorry, wherefore the angular momentum, we found that L had an integer for, I don't want to call this S, I want to call this S. Where S for orbital angular momentum, this would be L, and this would be an integer, but for spin angular momentum, we call, these are all the states we could build, all the towers we could build, which were, which were not expressible in terms of wave functions of a position on the sphere. Right? These are all the 1/2 integer states. So S could be 1/2, 3/2, 5/2, and so on. And then M sub S is going to go from minus S to S in integer steps, just like M for the orbital angular momentum L. So I want to talk about these states in some detail over the rest of this lecture and the next one. So the first thing to talk about is how we describe spin. So in principle, this is easy. What we want is we want to describe the state of a particle that carries this intrinsic angular momentum spin. So that's easy. The particle sits at some point. The problem is, it could be sitting at some point with angular momentum in the z direction, or with spin in the z direction, say plus 8 bar over 2. And let's focus on the case S is equal to 1/2. So I'll be focusing for the lecture for simplicity on the case total spin is 1/2, which is the two-state ladder, but all of this generalizes naturally. In fact, that's a very good test of your understanding. So for S is 1/2, we have two states, which I will conventionally call the up in the z direction and the down in the z direction. And I will often omit the subscript. If I omit the subscript, it's usually z, unless from context you see that it's something else. But so the wave function tells us the state of the system. But we need to know now for a spinning particle whether it's in the spin 1/2 up or spin 1/2 down state. And so we can write that as there's some amplitude that is in the plus 1/2 state of x and at position x. And there's an amplitude and it's at position x and it's in the minus 1/2 state or the down state. We again need that the total probability is 1. So another way to say this is that the probability that we find the particle to be at x with plus or minus h bar upon 2 being the spin in the z direction, so at x, spin in the z direction is h bar upon 2 plus or minus, is equal to norm squared of psi plus or minus of x. Okay. So this is one way you can talk about spin. You can develop the theory of spin nicely here, but it's a somewhat cumbersome formalism. So the formulation that I want to introduce is one which involves matrices and which presages the study of matrix mechanics, which you'll be using in 805. So instead, I want to take these two components. What we see already is that we can't use a single wave function to describe a particle that's spin 1/2. We need to use two functions. And I want to organize them in a nice way. I'm going to write them as psi is equal to, and I'll call this capital psi of x, is a two-component vector or so-called spinner, psi up of x and psi down of x. So it's a two-component object. It's got a top and bottom. And notice that its conjugate, or its adjoint, psi dagger, is going to be equal to psi up of its conjugate, psi down, a row vector, psi down, or a row spinner. And for normalization, we'll need that the total probability is 1, which says that psi capital dagger psi it says psi capital psi is equal to 1. But this is going to be equal to the integral dx. And now we have to take the inner product of the two vectors. So integral dx of psi up squared minus plus psi down squared. Cool? Yeah. The coordinate x is just representing position. So what I'm saying here is I have, again, we're going to mention this for simplicity. It's saying, look, if I have a particle that carries spin 1/2, it could be anywhere. Let's say it's at position x. So what's the amplitude at position x? And spinning up. I'm not going to indicate spinning down. Okay. So, I like my coffee. So that's what the of x indicates. So I've just been dropping the of x. Okay. So there's some probability that it's at any given point, and either spin up or spin down. Now again, it's important. Although I'm going to do this, we can eventually do this spin up, spin down. This spin is pointing in a vector space that's two-dimensional. It's either plus 1/2 or minus 1/2 h bar. So it's not like the spin is an arrow in a three-dimensional space that points. Rather, what it is, it's saying if I measure the spin along some axis, it can take one of two values. And that was shown in the Sturm-Gerlach experiment, where if we have a gradient of the magnetic field, dB, z, in the z direction, then we send, this is our Sturm-Gerlach box, and we send an electron in. The electron always comes out in one of two positions. Okay. Now this is not saying there's a vector associated with, that the electron has an angular momentum vector that points in this particular direction. Rather, it's saying that there are two possible values, and we're measuring along the z direction. Cool. So it's important not to make that mistake to think of this as some rotation, some three-dimensional vector. It's very explicitly a vector in a two-dimensional vector space. It's not related to regular rotations. Yeah.
Let me write that down.
Yes. Yeah, I haven't assumed their normalization, but each one could be independently normalized appropriately. Right, the whole thing has to be properly normalized, and writing it this way, this is just the... Good. Okay. So there's another nice bit of notation for this, which is often used, which is probably the most common notation, which is to write psi of x is equal to, well, psi up at x times the vector 1, 0 plus psi down of x times the vector 0, 1. Okay, so this is what I'm going to refer to as the up vector in the z direction. This is what I'm going to refer to as the down in the z direction vector. Okay. And that's going to allow me to write. All the operations we're going to need to study spin in terms of simple 2x2 matrices. Yeah.
Will those two sides not be the same?
Yeah, in general they're not. So for example, here's a situation, a configuration a quantum system could be in. The quantum system could be in the configuration particles here and spinning up. And it could be in the configuration particle over here and spinning down. And given that it could be in those two configurations, it could also be in the superposition over here and up and over here and down. Right? So that would be different spatial wave functions multiplying the different spin wave functions. Spin wave functions. That make sense? Okay, so these are not the same function. They could be the same function. It could be that you're equally, it could be either spin up or spin down at any given point with some funny distribution. But they don't need to be the same. That's the crucial thing. Other questions? Yeah. Yeah, so here's what we can say. We know that an electron which carries SZ plus e to the power 2 and a state corresponding to minus e to the power 2 are orthogonal, because those are two different eigenvectors of the same operator SZ. Right? So if these guys are orthogonal, up in the z direction and down in the z direction is orthogonal. And this is, thank you for this question. It's a good way to think about how wrong it is to think of up and down being up and down the z direction. Are these guys orthogonal? These vectors in space? No, they happen to be parallel with a -1 in overlap, right? So SZ is up and SZ is down are orthogonal vectors. But this is clearly not SZ is down, right? So the direction that they're pointing, the up and down, should not be thought of as a direction in three-dimensional space. It's just a different thing. What it does tell you is that if you rotate the system by a given amount, how does the phase of the wave function change? Right? So remember how the, we'll get into rotations in a minute, but what it does tell you is how the spin operations act on it, into your SZ acts with +1 half or -1. They're just different states. Yeah. It's similar to the story of polarizations, except polarizations are vectors, not spinors. It's similar in the sense that they look at spin-like vectors in three-dimensional space. They mean technically slightly different things. In the case of polarizations of light, those really are honest vectors, and there's a sharp relationship between rotations in space. But that's sort of quirk. They're both spin and vectors. These are not. Okay, so here's a notation I'm going to use. Just to alert you, a common notation that people use in direct notation is to say that the wave function is equal to psi up at x times the state up plus psi down at x times the state down. So for those of you who speak direct notation at this point, then this means the same thing as this. For those of you who don't, then this means this. Okay. So what I want to do is I want to develop a theory of these spin operators, and I want to understand what it means to be a spin 1/2 state. Now in particular, when I mean by develop the theory of the spin operators, if I was talking about orbital angular momentum, say the orbital angular momentum in the z direction, I know what operator this is. If you hand me a wave function, I can act on it with LZ and tell you what the result is. And then functions. And that means I can construct allowed eigenvalues, and I can talk about probabilities, right? But in order to do all that, I need to know how the operator acts. And we know how this operator acts. It acts as h bar upon I, dd phi, where phi is the angular coordinate around the equator, right? And so given any wave function, a function of x, y, and z, or r, theta, and phi, I can act with this operator and know how the operator acts. And it's true that, again, Lx with Ly is equal to I h bar Lz. Okay, it satisfies the same commutation relation as spin. But we know the spin operators cannot be expressed in terms of rate derivatives along a sphere. Right, I've harped on that many times. So what I want to know is what's the analog of this equation for spin? What is the representation of the spin operators acting on the spinners? Acting on states that carry half-integer spin. We know it's not going to be derivatives. What is it going to be? We're going to go with the goal. Okay, so in order to do that, we need to first decide just some basic definition of spin in the z direction. So what do the angular momentum operators do? Well, whatever else is true of the spin in the z direction operator, SZ acting on a state up is equal to h bar upon 2 up, and SZ acting on a state down is equal to h bar minus upon 2 down. And similarly, x squared on up or down. Oh, by the way, I'm going to relatively casually oscillate between the notations.
Let me just write this down. Spin operators in R over Z.
Up and plus up or down and plus or minus. Okay, so sometimes it'll write plus for up and minus for down. So I apologize for this into this. S squared on plus, this is the plus 1/2 state, is equal to h bar squared s plus 1, but s is 1/2, so 1/2 times 1/2 plus 1 is 3/4. H bar squared times 3 over 4. And we get the same thing up, ditto down. Okay, because s squared acts the same way on all states in a tower. Going up and down through a tower of angular momentum states, raising and lowering, does not change the total angular momentum because s plus and s minus can be with s squared, because they have exactly the same commutation relations as the angular momentum. Okay. That's an awesome sound. So I want to know what these look like in terms of this vector space notation, up and down. And for the moment, I'm going to dispense entirely with the spatial dependence. I'm going to treat the spatial dependence as an overall constant. So they're equally likely to be oppositions. Okay. So we can focus just on the spin part of the state. So again, I want to replace up by 1, 0 and down by 0, 1. And I want to think about how this looks. So what this looks like is SZ acting on opposition 1, 0 is equal to h bar upon 2, 1, 0. And SZ on 0, 1 is h bar upon 2, 0, 1. Okay. And s squared on 1, 0 is equal to 3 h bar squared on 4, 1, 0. And ditto for 0. Yeah. Oh, thank you. Yes, it really should. 3/4 good. Where that came from is that, remember that when we constructed the eigenfunctions of L squared acting on the state Lm was equal to h bar squared L plus 1, L plus 1 on phi Lm. Now, if we do exactly the same logic, which we actually did at the time, we did it in full generality, whether the total linear momentum was an integer or half integer. We found that if we took, I'm just going to use for the half integer state the symbol s, but it's exactly the same calculation. S squared on phi and again s m sub s is equal to h bar squared s plus 1 phi s m sub s. Okay, and so for s equals 1/2, then s plus 1 is equal to 1/2 times 3/2, which is 3/4. Good, yeah. But remember, does L go negative? Great. Does S go negative? No, S is just labeling the tower. So S is 0, it's 1, it's 2. And so, for example, here, these are states where S is 1/2, and the S in the z direction can be plus 1/2 or minus 1/2. S is 3/2, it can be, and then S in the z direction can be n is 3/2, 1/2, minus 1/2, minus 3/2. Cool? Okay. Other questions? Okay, yeah. Good, we're going to have to construct them. So, because what are they? Well, they lower in rates. So we're going to have to build the states that lower in rates. Awesome. So what did it mean that we had towers? Let me do that back here. So the question is, look, we're going to have to use the raising and lowering operators at the end of the day, but what happens if I raise the bottom state? What if I raise it down? I'll get up. And what happens if I raise up? You get 0. That's a statement that the tower ends. Right? On the other hand, if S is 3/2, what happens if I raise 1/2? I get 3/2. If I raise 3/2, I get nothing. I get 0 identically. And that's the statement that the tower ends. So for every tower labeled by S, we have a set of states labeled by M, which goes from minus S to S in integer steps. The raising operator raises us by 1, the lowering operator lowers by 1, the lowering operator annihilates the bottom state, the raising operator kills the top state. Cool? Yeah. Yeah, so do they have anything you can up and down? So up and down is just a name. I mean, it doesn't really communicate anything other than it's shorthand for spin in the z direction 1/2. And so so the question could be translated as, are there convenient and illuminating names for the spin free half states? And I don't really know. Yeah, I don't know. I mean, the states exist, so we can build nuclear particles that have them, free halves or 5 halves, all sorts of things, but I don't have a useful name. For the most part, we simplify our life by focusing on the 1/2 state. As you'll discover in 805, the spin 1/2 states, if you know them very, very well, you can use everything you know of them to construct all of the spin 5 halves, 8 halves, well, 8 halves is stupid, but 9 halves, all those from the spin 1/2. So it turns out spin 1/2 is sort of in a way that can be made very precise, and that's the theory of the algebras. Yeah.
So what is the usual elaborate what you meant by you really think of spin as like angular momentum vector?
Yeah. So, okay, good. So the question is, elaborate a little bit on what you mean by spin can be thought of as angular momentum vector. Spin certainly can be thought of as an angular momentum, because if the whole point here was that if you have a charged particle and it carries spin, then it has a magnetic moment, right? And a magnetic moment is the charge times the angular momentum. So if it carries spin and it carries charge and thus it carries magnetic moment, that's pretty much what we mean by angular momentum. That's as good a diagnostic as any. That this is meanwhile on top of satisfying that experimental property, this just as a set of commutational relations, these commutational relations are the commutational relations of angular momentum. It just turns out that we can have states with total angular momentum little s, which is half integral, 1/2, 3 halves, etc. Now the thing that I want to emphasize are twofold. First off, something I've talked on over and over again, so I'll attempt to limit my uses of this phrase, but you cannot think of these states with s as 1/2 as wave functions determining position on the sphere. Right. So that's the first sense in which you can't think of it as equivalent to orbital angular momentum. There's a second sense, which is that up and down should not be thought of as spin in the z direction being up and spin in the z direction being down, meaning pointing a vector in 3 dimensions pointing up and a vector in 3 dimensions pointing down, because those states are orthogonal, whereas these two 3-dimensional vectors are not orthogonal, they're parallel. Right? They have non-zero inner product. So up and down, the names we give these spin 1/2 states should not be confused with being pointing up in the z direction and down in the z direction. It's just a formal name we give to the plus 1/2 and minus 1/2 total angular momentum in the z direction states. Does that answer your question?
Yeah, so when you make a measurement value of spin, so perhaps you do a Stern Gerlach experiment and you get what the spin is. Can you not then say like, all right, this is spin plus 1/2 spin minus, like it's SC is positive 1/2, SC is minus 1/2.
Yeah, you can totally do, yeah, absolutely. So if you do a Stern Gerlach experiment, you can identify those electrons that had spin plus 1/2 and those that had spin minus 1/2. They come out in different places. That's absolutely true. I just want to emphasize that the up vector does not mean that they're somehow attached to the electron vector that's pointing in the z direction. Good. Yeah. Go ahead. What? Sorry. Yeah, that's an interesting question. So the question is, how do we know if an uncharged particle has spin? And there are many ways to answer this question. We have one of which is we're going to come to later, which has to do with Bell's inequality, which is a slick way to do it. But a very coarse way is this way: that we believe in a deep and fundamental way that the total angular momentum of the universe is conserved. In the following sense, there is no preferred axis in the universe. If you're a cosmologist, just stay out of the room for the next minute. So there's no preferred axis in the universe, and the laws of physics should be invariant under rotation. Now, if you take a system that has a bunch of particles with no angular momentum, and say, let me give you an example. Take a neutron. Okay, neutron has spin 1/2. And wait, how did I know that? We can do that experiment by doing the following thing. We can take a neutron and invite it to a proton and see that the resulting object has spin 1. Okay, so let me try to think what is a neutron. Granting for a moment, so let me show you one. It's going to take an example. Granting for the moment that you can take that you know that a neutron has spin 1/2. Okay, so let's just imagine that we knew that by hook or by crook. We then do the following experiment. We wait. Take a neutron, let it sit in empty space. When that neutron decays, it does a very cool thing. It decays into a proton and electron. Right? That you see the proton has positive charge, electron has negative charge, and it goes on. But you got a problem if you knew that the neutron has spin 1/2, and then you decay with the proton and electron. The total angular there is 1/2 is 1/2, or 1/2 minus 1/2 is 1 0, and you got a problem. Angular is going to be conserved. So what immediately deduce that another particle must have also been emitted that had half integer angular momentum, conserving angular momentum, and it couldn't carry any charge because the electron proton neutral, the neutron is neutral. So experiments of things like this, you can always deduce some conjugation of angular momentum one way or the other. But then the best way to do it at the end of the day is going to be some version of addition of angular momentum, where you have some object with electron proton, you allow them to stick together and start as those spin 1. Okay. Yeah. But we can talk about that in more detail afterwards. That's actually really good. Yeah. Yeah, okay, good. I don't want to get into this because it's a really good question. I don't know if I ask, or go to recitations and ask. It's a really good question. The question is this: look, angular momentum has a funny property under parity, under reflection. So if you look in a mirror, if this way, here's angular momentum, it's got right-hand rule, right? It's got angular momentum up. If I look in a mirror, it's going this way, right? So if you're to have the angular momentum down, right? That's what it looks like if you're reflecting in a mirror. Other direction. That's a funny property of angular momentum. It's also a true property of angular momentum. It's fine. What about spin? Is the question. Does the spin also have this funny property in parity? Is that basically the question? Yeah, and it does. And working out exactly how to show that is just sort of an entertaining exercise. So again, it's beyond the scope of the lecture. So come ask me off this after you're done. Yeah, one more. Yes. Yes. Absolutely. Yeah, those states are also orthogonal. That's exactly right. So again, even in the case of integer angular momentum, you've got to be careful about talking about the top state and the bottom state corresponding to pointing in some direction, right? Because they're orthogonal states. However, they do correspond to a particular angular momentum vector in 3-dimensional space. They correspond to a distribution on the sphere. So there's a sense in which they do correspond to real rotations, real time functions on the sphere, and there's also a sense in which they don't because they're still orthogonal. That's exactly right. Okay, so let me move on. I'm going to stop questions at this point. So Good. So far, these are the properties that need to be satisfied by our operators, and it's pretty easy to see in this basis, what these operators must be. SZ has eigenvectors 1, 0, and 0, 1. So SZ should be equal to a power 1, 2, 1, 0, 0, minus 1. So let's just check. This on 1, 0 gives me 1, 0. So it gives me the same thing back times h power upon 2. Cool. And acting on 0, 1, or the down state, we get h power upon 2 times 0 minus 1. That gives me minus 1. 1, 0 gives me 0. And 0 minus 1 gives me minus 1, which is 1 with minus sign. That's the minus sign. So this works out like champ. And s squared, meanwhile, is equal to, well, it's going to give me h bar squared times 3/4 for both of these vectors. So h bar squared. And meanwhile, these are eigenstates, h bar squared times 3 upon 4 times 1, 0, 0, 1. Okay. So what about, we know one other fact, which was brought up just a minute ago, which was that if you take plus 2, if you take s plus, and you act on the state 0, 1, what should you get? If you raise 0, 1, 1, 0, great, 1, 0. So we also worked out the normalization coefficient on the problem set, and that normalization coefficient turns out to be 1. Okay, and let's be careful, you got an h bar for dimensional analysis reasons. So meanwhile, s minus similarly on 0, 1 is equal to 0, and s plus on 0, 1 is equal to, oh, sorry, we already did that. We want s minus on 1, 0. Let's see, s minus on, we want s plus on 1, 0 is equal to, right, 0. And s minus on 1, 0 is equal to h bar 0, 1. Okay, so putting all this together, you can pretty quickly get that s plus is equal to, oops, we need an h bar, and we need it to raise the lower one and kill the top state. So on 1, 0, what does s plus do? That gives us 0, that gives us 0. Good. And on the lowered state, 0, 1, that gives me 1 up top, and that gives me 0 downstairs, so it works out this. So we got h bar. And similarly, s minus is equal to h bar times 0, 0, 1, 0. Okay. So we've got these guys. So much from just the definitions of raising and lowering. And by taking inner products, you can just derive those two lines from these. Okay. But notice that s plus minus, sx is equal to s plus s minus upon 2i, upon 2, and sy is equal to s plus minus s minus upon 2i. So this tells us that sx is equal to h bar upon 2 times s plus, we're going to get a 1 here, plus s minus, we're going to get 1 here, 0, 1, 1, 0. And s minus, or sy, sorry, is equal to, again, upon 2i times h bar upon 2i, times s plus, which is going to give me 1, and minus s minus, which is going to give me minus 1, 0, 0. But we can pull this I in. So 1 over I is like minus I. So minus I times minus 1 is going to give me I. And minus I times 1 is going to give me I. Okay. So, sorry, yeah, sorry, did I write I? That should be minus I. Thank you. So now we have a nice representation of these spin operations, of the spin operators. And explicitly, we have that Sx is equal to h bar upon 2, 0, 1, 1, 0. Sy is equal to h bar upon 2, 0, minus I, 0. And Sc is equal to h bar upon 2, 1, 0, 0, minus 1. Okay. So why is Sg the only one that's diagonal? Is it something special about Sg?
Z as the axis along which to project s squared.
Exactly. So the thing that's special about SZ is that at the very beginning of the day, we decided to work in a basis of eigenstates of SZ with definite values of SZ, right? So if they have definite values, then acting with SZ is just going to give you a number. That's what it is to be a diagonal matrix. You act on a basis, right? You just get a number out. Cool. So we started out with the assumption that we started out by working in the eigenbasis of SZ, and as a consequence, oh, that light is up. That was wrong. So as a consequence, we find that SZ is diagonal. And this is a general truth that you'll discover in matrix mechanics when you work in the eigenbasis of an operator. That operator is represented by a diagonal matrix. So we often say, rather than to work in an eigenbasis, we often say 2 diagonals. Yeah.
Because we had pretty sure 2i, and we initially had a 1 is operator and minus 1 above left.
Yeah, I'm pretty sure. So originally we had a downstairs I, right? So let's think about what this looked like. This was 1 and minus 1, right? Yeah. Agreed? So this is minus 1 over I. So we pull in the I. So we go from minus 1 to minus 1 over I. And we go from 1 to 1 over I. And I claim that 1 over I is minus I. Okay, and minus 1 over I is I. Is that cool? Good. Okay, so this is I and minus I. Okay, I always get that screwed, but it's useful to memorize these matrices. You might think it's a little silly to memorize matrices, but these turn out to be ridiculously useful. This is called sigma x. This is called sigma y, and this is called sigma z, and different people decide whether to put the 1/2 in there or not. The h bar does not go in there. Some people put in the 2, some people don't put in the 1/2. It's a matter of taste. Just be careful and be consistent. as usual. And these are called the Pauli matrices, because A, we really like Pauli, and B, Pauli introduced them. Although he didn't actually introduce them, in some sense, this mathematical structure was introduced ages and ages and ages ago. But physicists cite the physicist, not the mathematician. Okay, I'm not saying that's good. It's just saying it happens. Good, so notice the consequence of these. The important consequence of these, the whole point here was to build a representation of these spin operators. Now, whatever else the spin operators do, they can better satisfy that commutation relation. Otherwise, they're not really spin operators. That's what we mean by being spin operators. So let's check. Is it true that Sx commutated with Sy is equal to I bar Sc? So this is a question mark. Okay. Question mark. And let's check. Well, let's do the commutator. From the Sx, we're going to get an h bar upon 2. From the S1 from each Sy, we're going to get a factor of h bar upon 2. So I'll just write that as h bar upon 2 squared times the commutator of two matrices 0, 1, 1, 0. Commutator with 0 minus I 0. This is equal to h bar squared upon 4 times, let's write this out. The first one is going to be this operator, this matrix times this matrix. Well, that's going to be, again, a matrix. 0, 1, 0, 1, so that first one's a 1. 0, 1 minus I, oh, sorry, that's an I. Right, 0, 1, that's an I, that's a minus I. So 0, 1, 0, I gives me an I. 0, 1 minus I 0 gives me a 0. Second row, 1, 0, 0, I gives me 0. And 1, 0 minus I 0 gives me minus I. And then the second term is the flipped order, right? The commutator term. So we get minus the commutator term, which is going to be 0 minus I, 0, 1, that gives me minus I. 0 minus I, 1, 0, that gives me 0. Bottom row, I 0, 0, 1, 0, and I 0, 1, 0 give me I. Okay, so notice what we get. This is equal to h bar squared upon 4. And both of those matrices are the same thing. Those matrices are both I 0, 0, minus I with minus I 0, 0, I. Giving us I 0, 0, minus I times 2. For the two terms. The 2's cancel, and this gives me h bar squared upon 2 times I 0, 0, minus I. But this is also known as pulling out an I and an h bar. I, h bar. This is times h bar upon 2, 1, 0, 0, minus 1. This is equal to I h bar as z. Okay. So these matrices represent the linear momentum commutators quite nicely. Okay. And in fact, if you check, all the commutators work out beautifully. So quickly, just as a reminder, so what are the possible measurable values of Sz for the spin 1 half system? What possible values could you get if you measured Sz, spin in the z direction? Yeah, plus or minus h bar upon 2. Now, what about the eigenvectors? What are they of Sz? In this notation, there are these states. There's one eigenvector, there's the other. Let's ask the same question about Sx. So for Sx, what are the allowed eigenvalues? Well, we can answer this in two ways. The first way we can answer this by saying, look, there's nothing deep about z, which is the stupid direction we started with. We could have started by working with the eigenbasis of Sx, and we would have found exactly the same story. So it must be plus or minus h bar upon 2. But that's the reason you make that argument is A, it's like, and B, it's the only one you can make without knowing something else about how Sx acts. But now we know what Sx is. Sx is that operator. So now we can ask, what are the eigenvalues of that operator? And if you compute the eigenvalues of that operator, you find that there are two eigenvalues. Sx is equal to, and Sx is equal to h bar upon 2, and Sx is equal to minus h bar upon 2. Oops. These are h bar upon 2 and minus h bar upon 2. That's why I gave myself space. Sorry. And now we can ask, well, what are the eigenvectors? Now we know what the eigenvectors are because we can just construct the eigenvectors of Sx plus. And if you construct the eigenvectors of Sx plus, which, I'm not going to take the time. How many people want me to do the eigenvectors of Sx explicitly? Yeah, that's kind of what I figured. Okay, good. So the eigenvectors of Sx are, for example, on 1, 1. Sx on 1, 1 is equal to, well, Sx on 1, 1, the first term, that 0, 1 is going to give me a 1. The 1, 0 is going to give me 1. So this is h bar upon 2 coefficient of Sx on 1. And Sx on 1 minus 1 is going to give me h bar upon 2 minus 1 minus 1. Because all Sx does is swap the first and second components. So it gives me minus 1, takes it to the top, but that's just an overall minus sign. So again, we have the correct eigenvalues, plus or minus h bar upon 2, and now we know the eigenvector. So what does this tell us? What does it tell us that up in the x direction is equal to 1 over 2, if I normalize things properly, up in the z direction plus down in the z direction, right? That's what this is telling you. This is equal to h bar upon 2 times, well, actually, let me print this as, this vector is equal to up in the z direction, that's this guy, plus down in the z direction. Oops. But this isn't properly normalized, and properly normalizing it gives us this expression, 1/2. So what does this tell us? This tells us that if we happen to know that the system is in the state with angular momentum, or spin angular momentum, in the x direction being plus 1/2, then the probability to measure up in the z direction in a subsequent measurement is 1/2, and the probability to measure down is 1/2. If you know it's up in the x direction, the probability of measuring up in the z or down in the z are equal. You're at chance. You're even odds. Agree with that? That's the meaning of this expression. And similarly, down in the x direction is equal to 1 over root 2 up in the z direction minus down in the z direction. And we get that from here. This state is explicitly, by construction, the eigenstate of Sx, as we constructed Sx, and we have general expression in terms of the z eigenvectors up and down. That's what this expression is giving us. It gives an expression of the Sx eigenvector in the basis of Sc eigenvectors. Cool? So, for example, this tells you that the probability to measure up in the x direction, or in the z direction, given that we measured down in the x direction first, so this is the conditional probability. Suppose I first measured down in the x direction, what's the probability that I subsequently measure up in the z direction? This is equal to, well, it's the norm squared of the expansion coefficient. So, first up in the x direction, or sorry, down in the x direction, and the probability that we're up in the z direction is 1 upon root 2 squared. Usual rules of quantum mechanics. Take the expansion coefficient, take its norm squared, that's the probability. And we call that 1/2. Cool? And we can do exactly the same thing for Sy. So let's do the same thing for Sy without actually working out all the details. Okay. So doing the same thing for Sy, up in the y direction is equal to 1 upon root 2 times up in the z direction plus I down in the z direction. And down in the y direction is equal to 1 upon root 2 up in the z direction minus I down in the z direction. And I encourage you to check your knowledge by deriving these eigenvectors, which you can do given our representations of Sy. Very cool? Now here's a nice thing that we're going to use later. Consider the following. Consider the angle, the operator s theta, which I'm going to define as cosine theta Sc plus, oh sorry, I'm not even going to write it that way. So what I mean by s theta is equal to take our spherical directions and consider an angle in the, this is x, let's say y, x, z. Consider an angle theta down in the zx plane. Okay. Theta. And we can ask, what is the spin operator along the direction theta? Right? What's the angular momentum in the direction theta? If theta, for example, is equal to pi upon 2, this is Sx. Cool. So I'm just defining the spin operator, which is the angular momentum along a particular direction theta in the xz plane. Everyone go with that? This is going to turn to be very useful for us, and I encourage you to derive the following. And if you don't derive the following, then hopefully what we've done in your recitations is, well, I will tell you the recitation circuit. And if you do this, then what are we going to get for the eigenvalues of s theta? What possible eigenvalues could s theta have? Good, why? Fabulous. Okay, so the answer is that was given is that it's the same plus or minus h bar upon 2 as Sc, or indeed as Sx or Sy, because you can't possibly matter what direction you chose at the beginning. I could have called this direction theta z. How do you stop me? Right? We could have done that. We didn't. That was our first way of answering. Second way of answering is what? Well, construct the operator s theta and find its eigenvectors and eigenvalues. So I encourage you to do that. What you find is that, of course, the eigenvectors, the eigenvalues are plus or minus h bar upon 2, and up at the angle theta is equal to cosine of theta upon 2 up in the z direction, plus sine of theta upon 2 down in the z direction. And down theta is equal to cosine theta upon 2 up in the z direction, minus sine of theta over 2 down in the z direction. Oops, no, I got that wrong. This is sine, and this is minus cosine. Good. That makes more sense. Okay, so let's just check the sanity check. These guys should be properly normalized. So we take the norm squared of this guy. The cross terms vanish because of z and down 0 orthogonal states. So we're going to cos squared plus the sine squared, that's 1. So that's properly normalized. Same thing for this guy. The minus doesn't change anything because we norm squared. Now let's check that they're orthogonal. We take this guy down into this guy, everything's real, so we get a cosine from up, we're going to get cosine sine, and from down, we're going to get minus cosine sine, so that gives us 0. So these guys are orthogonal, they satisfy all the properties we want. So this is a good check. Do this. Of your knowledge. And if we had problem sets allowed this, we can give you this in your problem set. But we do. So suppose now, suppose that I measure, so I want to use these things for something. Suppose that I measure SZ and find SZ is equal to 1/2 h1 plus h bar equals 2. Okay? At some moment in time. First question is easy. What's the state of the system subsequent to that measurement? Man, you're so quiet today. What's the state of the system subsequent to measurement that S at Z is plus h bar upon 2? Up Z, good. So our state, psi, is up Z. Upon measurement. Okay? After measurement. And if I measure Sx, so 1, 2, measure Sx, what will I get? Okay. What values will I observe with what probabilities? Well, first off, what are the possible values that you can measure? Right, the possible eigenvalues, so which is plus or minus h bar upon 2, but with what probability? Exactly. So we know this from the eigenstate of Sx. If we know that we're in the state of z, we can take linear combinations of this guy to show that of z is equal to 1 over root 2. So let's just check. If we add these two together, up x and down x, we add them together, we'll get 1 over 2, 1 over 2, 2 over 0. Root 2 times of z is up x plus down x. Up x plus down x, dividing through by 1. So here we express the up in the z direction in the basis of x and y, which is 1. So students, the probability that I measure plus 1/2 as x is equal to plus 1/2 h bar upon 2 is equal to 1 over 2 squared, so 1/2. And ditto Sx is equal to minus h bar upon 2, same probability. Okay. What about Sy? Again, we have one of two values, plus or minus h bar upon 2. Probability of measuring plus is equal to 1/2, and the probability that we measure minus 1/2 is 1/2. That's h bar upon 2. Okay. So this should look familiar. Going back to the very first lecture, hardness was spin in the z direction, and color was spin in the y direction, or in the x direction. And we added at one point a third one, which I think I called whimsy, which is equal to spin in the y direction. Okay? And now all of the box operations that we used in that very first lecture, you can understand is nothing other than stringing together chains of string-Gerlach experiments doing Sx, Sy, and Z. So let's be explicit about that. Take that concrete. Actually, let's do that here. So for example, suppose we put a random electron into an Sx color box, or a Z color box. Okay, some are going to come out up, and some are going to come out down in the Z direction. And if we send this into now an Sx color box, okay, this is going to give us either up in the x direction or down in the x direction. And what we'll get out is 50-50, right? Okay, so let's take the ones that came out down. And if we send those back into an SZ, what do we get? Yeah, 50-50, because down x is 1 over 2 up Z plus 1 over 2 down Z. What was going on in that very first experiment where we did hardness, color, hardness? Superposition. And what superposition was a hard electron? It was 1 over root 2, white plus black. We know precisely which superposition. Here it is. Okay. And now let's do that last experiment where we take these guys, Sx down, and I'm writing this upside down. Beam joiners. We take the up in the x direction and the down in the x direction, and we combine them together and we put them back into Sx or Sz. What do we get? Well, what's the state? 1 over root 2 down x plus 1 over root 2 up x. It's up Z. Up Z into an SZ color box, or SZ box, what do we get? Up Z 100%. That's white with 100%. Or hard with 100%. Sorry. Oh, I put it down. Shoot, I'm sorry. Well, yeah, indeed. I meant to put it up. Yes, yeah, we'll see. 100% confidence. If we remove the mirror, 50-50. If we add in the mirror, 100%. And the difference is whether we're taking one component of the wave function or whether we're superposing them back together. Okay? Imagine we know we have a system in this state, and I say, look, this component is also coincidentally very far away, and I'm going to not look at them. So of the ones that I look at, I have 1 over root 2 of x. But if I look at the full system, the superposed system, that adds together to be an eigenstate of SZ. These are our color boxes. Yeah?
I don't know what each of the where it's like sort of have their two states together.
Yeah, excellent. This is a very solid point. So here we have to decide what we mean by the beam splitter, and what I'm going to mean by the beam splitter or by the mirrors and beam joiners. So the question is, how do we know that it does this without changing the superposition? What I want to do is define this thing as the object that takes the two incident wave functions and it just adds them together. It should give me the direct superposition with the appropriate phases and coefficients. So if this was plus of x, then it stays plus of x. If it's minus of x, it's going to be minus of x. Whatever the phases of this state, when it gets here, it just adds together the two components. That's my definition of that adding box.
So realistically, what that look like?
Oh, what, you think I'm an experimentalist? Look, every time I try an experiment, I get hit by a shark. Okay, so yeah, no. How you actually implement that in real systems is a more complicated story. So you should direct that question to Matt, who's a very good experimentalist. Okay, so finally, let's go back to the Stern-Gerlach experiment, and let's actually run the Stern-Gerlach experiment. I guess we'll do that here. So let's think about what the Stern-Gerlach experiment looks like in this notation, and not just in this notation, in the honest language of spin. I'm going to do a slightly abbreviated version of this, because you guys can fill in detail through your knowledge of Ada 2 and Ada 3. Okay, so here's the Stern-Gerlach experiment. We have a gradient in the magnetic field. This is the z direction. We have a gradient where b in the z direction has some b naught, a constant plus beta z. Okay, so it's got a constant piece and a small gradient. Are we cool with that? So it's just the magnetic field gets stronger and stronger in the z direction. There's a constant, and then there's a rate of increase in the z direction. Now I'm going to send my electron through. And remember, my electron has a wave function, so my electron is equal to what's that some amplitude to be up? A up Z plus some amplitude B down Z. And if this is a random electron, then its state is going to be random, and A and B are going to be random numbers whose inner squared add up to 1. Part normalization. Cool. So here's our random initial state. We send it into this region where we've got a magnetic field gradient, and what happens? Well, we know that the energy of an electron that carries some angular momentum is a constant mu naught times its angular momentum divided into any ambient magnetic field. This is just saying that. This is saying that magnets want to anti-align. Now, here we've got a magnetic field in the z direction. This is minus mu naught. Z, BZ, and BZ was a constant beta naught plus, B naught plus beta Z. Okay. So the energy has two terms. It has a constant term which just depends on its Z, and then there's a term that depends on Z as well as depending on its Z. So you can write this as A. So SZ, remember what SZ is? SZ is equal to H bar upon 2. 1, 0, 0, minus 1. So this is a matrix with some coefficient up. How do I want to write this out? Yeah, I guess you don't really need to write this out. But this is a matrix, and this is our energy operator. And it acts on any given state to give us another state back. It's an operator. Okay. And importantly, I want this to be only, this is in some region where we're doing the experiment where we have a magnetic field gradient, and outside of this region, we have no magnetic field and no magnetic field gradient. So it's 0 to the left and 0 to the right. So as we've talked about before, the electron feels a force due to this gradient in the magnetic field. The energy depends on Z, so the derivative of the energy with respect to Z, which is the force in the Z direction, is non-zero. But for the moment, that's a bit of a red herring. Let's just focus on, instead of worrying about the center mass motion, let's just focus on the overall phase. So let's take our initial electron with this initial wave function A up Z plus B down Z, and let's note that in this time. So what does this matrix look like? Okay, so fine, let's actually look at this matrix. So SZ is the matrix 1, 0, 0, minus 1 times H bar upon 2. So we have H bar upon 2 mu naught minus mu naught, and then B naught plus beta Z, which I'll just write as B, which is equal to some constant C 0, 0, some constant minus C. Everybody agree with that? Where constant just means it's a number, but it doesn't depend on Z. It's the Z. Now here's the nice thing. When we expand the energy on up Z, this is equal to C Z up Z, because there's our energy operator. And energy on down Z is equal to minus CZ of Z down Z. So up and down in Z direction are still eigenfunctions of the energy operator. We've chosen an interaction, we've chosen a potential, which is already diagonal, so the energy is diagonal. It's already in its eigenbasis. So the consequence, this is the energy of the up state is equal to, in the Z direction, is equal to plus C. And energy in the down state, is equal to minus C. Everybody agree with that? So what this magnetic field does is it splits the degeneracy of the up and down states. The up and down states originally had no energy splitting, they were both zero energy. We turn on this magnetic field, and one state has positive energy, and the other state has negative energy. So that degeneracy has been split. Where did that original degeneracy come from? Why did we have degeneracy in the first place? Spherical symmetry. And we turn on the magnetic field, which picks out a direction, and we break that degeneracy and we lift the splitting. Okay? So here we see that the splitting is lifted. Now we want to ask, how does the wave function evolve in time? So this was our initial wave function. Well, we know from the Schrödinger equation that psi of t is going to be equal to, well, those are already eigenvectors, so A, e to the minus I, e up t upon 2, or upon h bar, up z, plus B, e to the minus, e the minus I, e down t upon h bar, down z. Okay. We can write this as equals A, e to the I, mu naught, B naught, t over 2 plus I mu naught beta t z upon 2 up z plus b same e to the minus I. Oops, that should be, oh, that's plus. That's e to the I mu naught b naught t over 2. And we write this as two exponentials. E to the minus I mu naught beta t z upon 2. Oh no, that's minus good. Okay. Down z. Okay, so what is this telling us? So what this tells us is that we start off in a state which has some amplitude b up and some amplitude b down, A and B. And at a later time t, psi of t, what we find after we run it through this apparatus is that this is the amplitude. What do you notice? Well, we notice two things. The first is that the system evolves with some overall energy, so the phase rotates as usual. These are energy eigenstates. But the amount of phase rotation depends on z. So in particular, this is e to the I some number times z. And what is e to the I some number times z? If you know you have a state that's of the form e to the I some number, which I will, call kz times z, what is this telling you about the system? This is an eigenstate of what operator? Momentum in the z direction carries one momentum. H bar kz, exactly. So what about this? If I have a system in this state, what can you say about its momentum in the z direction? Well, it's not zero, right? Here's a z. These are a bunch of constants. It's beta, t, mu naught 2, I. So it's not zero. In fact, it's got minus some constant times z. Right? So this is a state with negative momentum. Everyone agree? It's got momentum z down in the z direction. What about this guy? Momentum up. So the states that are up in the z direction get a kick up. And the states that are down in the z direction get a kick down. They pick up some momentum down in the z direction. Yeah. A big T should be little t. Sorry. Yeah, handwriting there. That's just t. Yeah.
So in this case, the eigenvalue is a function of t. That's allowable.
Yeah, that seems bad. But remember what I started out doing? Oh, did I erase it? Should we erase it? So we started out saying, look, the wave function is up in the z direction, or really rather here, up in the z direction times some constant. Now in general, this shouldn't be a constant. It should be some function. So this should be a function of position times up in the z direction. This is a function of position times down in the z direction. So what we've done here is we said under time evolution, that function changes in time, but it stays, something combination up and down. So you can reorganize this as the time evolution equation here is an equation for the coefficients of up z, the coefficients of down z. Other questions? Okay, so the upshot of all this is that we run this experiment, and what we discover is that this component of the state that was up z gets a kick in the plus z direction, and that those electrons, any electron that came from this term of the superposition will be kicked up z, and any electron that came from the superposition down z will have down. And what we really mean is not that an electron does this or does that, but rather that the initial state of an electron that's here with the superposition of z up and down ends up in the final state as a superposition of up z being up here and down z being down here. Okay? An electron didn't do one, it didn't do the other. It ends up in a superposition, so the state again. So what this String-Gerlach experiment has done, apparatus has done, is it's correlated the position of the electron with its spin. So the problem, if you find the amplitude defined up here and down is very small. The amplitude defined up here and up is very large. Similarly, the amplitude defined down here and up is 0. The amplitude defined down here and up, and down is large. Cool? So this is exactly what we wanted from the boxes. We wanted not to do something funny to the spins, we just wanted to correlate the position with the spin. So the final state is a superposition of these guys, and which superposition is exactly this superposition? So these calculations are gone through the notes that are going to be posted. Okay. So questions at this point? Yeah.
So you put the electron to the String-Gerlach device, is that kind of
Excellent. When you put the electrons through the String-Gerlach device, do they come out with a definite position? No, at the end of the experiment, they're in a superposition of either being here or being here. And they're in a superposition of either being up spin or down spin. Have we determined the spin through putting it through this apparatus? No, we haven't done any measurement. The measurement comes when we now do the following. We put a detector here that absorbs an electron. Yeah, I got hit. And then you've measured the momentum by measuring where it came out. If it comes out down here, it will be in the positive. So this is a nice example of something called entanglement. And this is what we're going to pick up next time. Entanglement says the following. Suppose I know one property of a particle, for example, that it's up here. Suppose I'm in the state, psi is equal to up. And pointed up, so up here, and up in the z direction, plus down there, and down in the z direction. Okay? This means that at the moment, initially, if I said, look, is it going to be up or down with equal probabilities, 1 over 2? With equal to. If I measure spin in the z direction, what value will I get? What values could I get if I measure spin in the z direction? Plus or minus 1/2. What are the probabilities that I measure plus 1/2 and minus 1/2? Even odds, right? We've done that experiment. On the other hand, if I tell you that I've measured it to be up here, what will you then deduce about what its spin is? Always plus 1/2. Did I have to do the measurement to determine that it's plus 1/2? No, because I already know the state, so I know exactly what I will get if I do the experiment. I measure up here, and then the wave function is this, so that's 1 over 2. I'll measure it. As a consequence, if I subsequently measure up here, the only possible value is up in the z direction. Yeah? This is called entanglement. And here is entanglement of the position with the spin. And next time what we'll do is we'll study the EPR experiment, which says the following thing. Suppose I take 2 electrons. Okay? Take 2 electrons, and I put them in the state. One is up and the other is down, or the other is, the first is up and the second is down. Okay? So up, down, plus, down, up. Okay? I now take my 2 electrons and I send them to distant places. Suppose I measure one of them to be up in the x direction. Yeah? Then I know that the other one is down in that direction. So if I measure up in the z direction, I determine the other one is down in the z direction. But suppose someone over here who's causally disconnected measures not spin in the z direction, but spin in the x direction. They'll measure one of 2 things, either plus or minus. Now, knowing what we know, that it's in a z eigenstate, it will be either plus x, but plus 1/2 in the x direction, or minus 1/2 in the x direction. Suppose I do both measurements. The distant person over here doesn't measure the z and says, aha, mine is up, so the other one must be down. But the person over here doesn't measure z, they measure sx or s, they measure sx, and they get that it's plus sx. And what they've done as a result of these 2 experiments, Einstein, Podolsky, and Rosen say, is this electron has been measured by the distant guy to be spin z down, but by this guy to be measured spin x up. So I know sx and sz definitely. But that flies in the face of the uncertainty relation, which tells us we can't have spin z and spin x, definitely. Einstein, Podolsky, and Rosen say There's something missing in quantum mechanics because I can do these experiments and determine that this particle is Sx down and Sz down and Sx up. But quantum mechanics says that once I've done the measurement of what quantum mechanics says is that I may have done the measurement of Sz, but that hasn't determined anything about the state over here. There's no predetermined value. What we need to do is we need to tease out, we need an experimental version of this tension. The experimental version of this tension, fleshed out in the EPR experiment, is called Bell's inequality. We studied it in the very first lecture. I'm going to show its violation in the next lecture. See you guys next time.
All right, one more lecture.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So to finish up, today I want to finish up a couple of loose ends of the class. The first is I want to pick up. By the end of the day, we'll talk about EPR that we picked up in the last couple of lectures. We're going to close up Bell's theorem from the very beginning. So we talked about Bell's inequality, and we'll reprove Bell's inequality, and then we'll see what quantum mechanics has to say about it. But first, I'm going to show you something neat. So a couple of times we talked about entanglement and what it can do, and I want to spend the first good chunk of the class talking about what entanglement can do. So before we get started, I want to remind you of a couple things in the last lecture. So the first is particles can have spin, half-integer, intrinsic angular momentum. That has nothing to do with being a rigid object that rotates, but it's just an intrinsic property of angular momentum. And the spin is represented, it's observable, it's represented by an operator. In fact, the vector operator says x, y, and z that satisfy the same commutative relations as the orbital angular momentum. And last time, one thing we showed is that a state which is up, or for example, down at an angle theta, so if I measure the spin along this axis, I will always find it's either up or down, spin 1/2, plus 8.2 or minus 8.2. But I can express this state in terms of the states with spin which are up or down along the z-axis. And we found, we gave an expression, and I challenge you to follow the logic given to derive this expression. An expression for the state which is in this case down along the angle theta, down when measuring spin along the angle theta, in terms of up and down along of spin along the z-axis or along the angle 0, theta being the declination from vertical. Okay? Yeah. Yes. Yes. Yeah, there's a general thing for this that says for a general angle, and it's actually in the notes, which I guess weren't posted from last time, but there it is in the notes. It's also easy to derive, right? Just you know what's the point here? The point is you have a spin vector, and it's a vector s, x, y, z, and you can compute the operator representing spin along a particular direction by taking a unit vector in that direction and taking the dot product. So that gives you a particular linear combination of s, x, y, and z. But from last time, that's just some stupid matrix, and you can express that matrix in any basis you want. For example, the basis of down the z direction, which is what we used last time. And then you can find the eigenvectors of that. That's how you find these states. Yeah. So there's very simple generals. It just involves an extra angle theta, which is the angle around the equator. Okay. So then, sorry, phi. I'm starting with phi. So we then did the following thing. I talked about the Stern-Gerlach experiment, and here I'm going to abstract away from the Stern-Gerlach experiment the core of the nugget, the core of it. The core of it is this. Suppose I have some spin, and I put it in a particular state. Let's say, for simplicity, up in the z direction plus down in the z direction with equal amplitudes. So they're equally likely to be measured. And then, so these two states should be degenerate in energy because the system is rotational invariance, just a spin sitting there. There's rotational invariance, so we know that the energy can't depend on the z component of the angular momentum. But we can break that symmetry and break the degeneracy by turning on a magnetic field. So for Stern-Gerlach experiment, we turn a magnetic field that had a gradient, but I just want to look at a constant magnetic field for the moment, see what it does. So we turn on a constant magnetic field, that's a contribution of the energy, which is minus the magnetic field dot the magnetic moment, which is a constant times the spin. But if the magnetic field is in the z direction, then it's just dz sc. So we then found yesterday that this led to a splitting, that the upstate had energy plus h bar omega, and the downstate had energy minus h bar omega, where omega is combined mu naught dz upon 2. Yesterday we had an additional term which involved the z dependence, the beta z term. But here I'm just looking at a constant magnetic field. But if we know what the energies are, these are still the eigenstates of the energy operator. If we know what the energies are, we know how the system evolves in time. Here's the initial state. These are the eigenstates. The energies are these. So we can let the system evolve in time, and we find that all we do is we evolve the system with phases. This is as usual in quantum evolution. If you have an expansion of a state in energy eigenstates, time evolution is just phases for each term. But note that there's a simple thing. This omega, the thing that determines the rate of evolution of the phase, is controlled by a magnetic moment, which is something intrinsic to spin, and a magnetic field, which is something I can dial in an experiment. I can really tune. Meanwhile, you decide how long to leave the magnetic field on. I can turn the magnetic field on for a while, I can turn it off a while later. So suppose I leave the field on for a time t such that omega t is equal to pi upon 2. Okay, so I turn on the magnetic field for a time t such that omega t is pi upon 2, or t is equal to pi upon 2 omega. What is the state then afterwards? The state subsequently, psi after, is equal to, well, it's this guy with omega t equal to pi upon 2, but let's give the I pi upon 2, I, and give it by pi over 2, minus I. So this is an I and minus I. I can pull out the i's, but phi after is I phase upon root 2 times up z minus down z. Yeah? That's cool. And this is a state that we saw last time. It's actually up to normalization, which is just an I, up or down x, down the x direction. Okay. So what this lets us do is something really quite cool. What this tells us that all these conditions are just the Stern-Gerlach calculations, but even easier because we don't have a gradient. If we have the spin in some superposition, which incidentally was initially up and down in the z direction, this is equal to up in the x direction. And we turn the magnetic field in x, we have it up. We turn the magnetic field in z, and what happens is the spin precesses around the z-axis, and we get down. Okay? We get precession. Here's the important point. the important point for everything that's going to follow is this. If I have some spin state, and I want to take it to some other spin state, how do I do so? Well, I can build a machine that does it by turning on the appropriate magnetic field and having the magnetic field presets the spin. Okay?
Let me just put
Here I found exactly what magnetic field I need to turn on, what amplitude and for how long, so that I take the state up x to down x. It's the known phase of it. Everyone with that? So any unit, here's the thing I want to get into, any unitary operation that takes you from one vector to another vector, or from one spinner to another spinner, up z, down y, linear combination of up and down z, some particular linear combination of up and down x. Any such pair of vectors can be related by unitary transformation, and any such unitary transformation can be built by some series of magnetic fields. Like, cool? And you can prove this yourself quite quickly, but let me just state it. Okay. So now this gives us the ability to do the following. One, so what do we have here? When we have spins, one, spins that can be put in a system, that can be put in states like up z and down z. Right? And two, the ability to rotate states, ability to evolve states from state to state, from spin state 1, side 1 to side 2, by turning on some magnetic fields. So by suitably choosing a magnetic field. Ever recall that? So here's the question I want to ask: what do we do with this? Imagine we really had this equipment in front of us. What power, what awesomeness can we realize? And this is the entry point to quantum computing. The answer to what can you do with this cool machinery is you can build a quantum computer. So let's talk about what that means. So quick question, do quantum computers exist? Yeah, are they very big? You know, okay, the biggest quantum computer that's been built to my knowledge is one that has factor the number 15, although they might get 21 at this point. I'm not exactly sure. It's 21? Yeah, I'll get 21 stuff. Good. So that's the upper end of the limit. Yeah. Well, they're large physically. It's true. They take up a room, but at least a large tabletop, an optics table. But they're not very big in a useful sense. Okay. And there's actually interesting, reasonable people, not just reasonable, intelligent people, and reasonable. That's not trivial. Okay. The people who live at the intersection of intelligent and reasonable. Okay. Which admittedly, as my colleagues pointed out, is not a large overlap. There are people in that overlap who suspect that it's for some fundamental reason impossible to build a useful quantum computer in some deep sense. I don't know whether that's true or not, but we're about to engage in a discussion of what happens when you build quantum computers for n bits where n gets large, like millions and billions as you need for codes or for studying images. And of course, it's a little strange because such a computer doesn't exist, which leads to my colleague and friend Scott Aaronson's lovely comment that his job as someone who studies quantum computers is to prove things that can't be done with computers that don't exist, which is what we're about to do. So let's talk about quantum computing. So what are we doing quantum computing? Here's the basic idea. Let's talk about classical computing. Classical computing says I have these things called bits, which are binary objects. They're either 0 or they're 1. And we realize in a very particular way, we realize them with a little magnet, which points north or south. Now it's not always exactly a magnet. It isn't like an old style hard disk. In your computer, it's something a little more fancy than just a magnet, but it's still basically a magnet. And you have something north south, and whether it's pointing north first, whether it's pointing south down here, which I'll call 0, or whether it's pointing north down here. Which I'll call 1, determines whether you call this 0 or 1. And classical computation is your data are a set of numbers, what's pointing down. And the process of doing a classical computation is build a machine which is governed by classical mechanics, okay, that takes this initial configuration and replaces it with a new one, f of 0, 1, which is also some number, so maybe it's 0, 0. I don't know, whatever f is. And what you want to do is you want to perform some calculation, which is some function, a known function of your input variables, function in this case of 2 bits, which produces the output that you want, and you build a machine that does that. Okay, so let me give you an example. I want to build a classical computer that takes a string of binary integers 0, 0, 1, 0, 0, and perform the logical law on each bit independently. So I need to build that computer out of objects available to me. Okay, and it needs to use nothing other than the laws of classical mechanics that has to suffice to describe the system. So let me give you an example of such a computer. Right, Alan, why don't you do this calculation? Okay, so that's the input, and I am now the classical computer 0011. Right? Now that's not actually what you do in your cell phone or on your laptop. That uses transistors, but it's the same basic idea. You build a set of machines, you build a set of objects, magnetic fields, electric currents that affect this calculation. And so there's some relationship between what electric fields you turn, what currents you induce to flow, and the calculation you want to perform F of V. Okay, this is the basic idea of a classical computer. With a quantum computer, we want to, and one last thing, suppose we have n bits. Suppose we have n classical bits. Then we have 0, 1, at the end. And how many numbers do you have to specify? Specify the configuration of n bits. This is sort of
Zad Granite, I think is the name, asking if I made any improvement over last week. Well, I've covered a lot more material. This is the last class and we're finishing it up right now. And so I've definitely learned a lot more things. I think that there's a lot more depth, but sort of what we did is we were kind of did the first pass of the first 10 lectures, and we've done now the first pass of the whole circuit. So I don't know whether I've gotten that much better at the stuff from lecture 0 to 10, although obviously we've gone deeper with it. So even just listening to these lectures, I can see now things that weren't as obvious in those first lectures. But at the same time, so it's, I wouldn't say it's so much improvement as I've learned different things that now need to be improved.
Well, no, you just need to specify the number of each bit, right? So we need n bits, right? So n binary numbers. Remember that? I specify what each register is. No. Okay. Let's treat, imagine this is quantum mechanical. Let's now take, instead of having bits, let's take quantum mechanical bits, by which I'm going to mean a system that has two possible observable states, 0 and 1. Okay, so these are the possible observable states. To specify a general configuration, I say that psi is equal to, and I'm going to represent this by, so psi is equal to some linear combination, alpha 0 plus beta 1. Now, if I measure, we know that we'll find either 0 or 1. If we measure the spin in the z direction, we'll measure either up or down. However, at a given moment in time, the system needn't be in a state corresponding to a definite value, that it could be in a general superposition. Agreed? So now here's the question. How many numbers does it take to specify the state of a single quantum bit? 2 complex numbers. Right? It takes 2 complex numbers to specify the state of the bit. And if we have n qubits, and there are n of these guys, well then, how many numbers does it take? Well, I have to specify the state of every possible, I have a possible superposition for every possible configuration of the system. So for example, yell 0, 0, 0, 0, plus beta, the first one is 1, the rest are 0, plus, and how many terms are there? There are 2 to the n terms. Right? So how many numbers do I need to specify this to the state of n qubits? I need 2 to the n complex numbers. Yeah? Everyone see that?
A sec.
So this immediately leads to a really frustrating reality you have to face. Suppose you want to simulate, using a classical computer, such as sits on my desktop, I wanted to simulate a quantum mechanical system of n bits, or n spin 1/2 states, evolving according to some energy function, evolving according to some Hamilton. How many variables and how much memory will it take? 2 to the n, right? If I've got n bits I want to describe, it's going to take 2 to the n complex numbers. So that's how many variables I have. So if I have 10 bits, literally 10 little spin 1/2 objects, to accurately specify the quantum configuration of the system, I need 2 to the 10 complex numbers. And that's for 10 spins. How many spins make up this piece of chalk? Right? So could you ever, in an honest way, simulate on a computer, on a classical computer like sits on my desktop, a quantum mechanical system the size of this chalk? Absolutely not. It's completely and utterly intractable. You have to come up with some sort of approximation scheme. So simulating quantum systems directly by just taking the spins and representing them with a wave function is wildly inefficient, incredibly difficult. Interestingly, the converse is almost certainly not so difficult. It's almost certainly possible for a quantum system to simulate classical evolution quite easily. How do you know that? Yeah, here we are, exactly, right? Nature apparently has no trouble simulating classical mechanics with underlying quantum mechanics. Quantum mechanics is the operating system, and classical mechanics is the simulation for it. Okay? Yeah, in a very useful sense, very real sense. So at this point, Feynman, I think, was the first person who really pointed this out, but I don't know the details of the history, but the lore is that this was really Feynman's observation, that, look, if that's true, this opens up a real possibility for computation. If things like spins, hard problems like calculating how spins evolve, or even the motion of chalk through the room, can be done pretty efficiently by nature, if we could build a computer that used quantum mechanical bits, whose variables were quantum mechanical and involved all the superpositions and interference effects of quantum mechanics, perhaps we could build computers that run exponentially faster and with exponentially less memory and less resources than a classical computer would. Because apparently it works, right? Because we're here, as was said. So this is the question of quantum computing. Can you use quantum mechanics? Can you use in particular the quantum evolution of the system to perform calculations that you care about rather than classical computations? And if you do so, do you gain anything? Do you get any sort of speed up? Is there an enhancement? Is anything better? So here's the basic gig. The basic gig is that we're going to take our system, consider the following kinds of quantum systems. Our systems are going to be n qubits or n spins. But because I want to emphasize that the substrate doesn't matter, the underlying material doesn't matter, I'm going to refer to them purely, and this is totally typical field, as qubits rather than spin systems. So the reason is it might work to use little isolated, spinning particles with intrinsic spin. That might turn out to be technologically infeasible. It shouldn't matter at the end of the day. In the same way that if I ask you, how does your computer work? If I ask you to write code, you write some code in C or Python or whatever, if you're choosing these. So you write some little scheme code. I still love scheme. You write some little scheme code, and it performs some calculation. It's defined in just logic, and you have this in abstract logic. Do you need to know the substrate? Do you need to know whether your transistors are built out of silicon or germanium, or indeed whether it's running on vacuum tubes? No, that's the whole point of abstracting away computation, that the substrate doesn't matter. So we can use spin 1/2, and that's going to be useful for us at various moments. But I want to emphasize that the important thing is the actual logic of the process, not the underlying substrate. So here's what I mean. My systems are going to be n copies, or n qubits, where each bit is specified by either 1, represented by up, or 0, represented by down. I'll use these interchangeably. So that the full system, psi, is a superposition of sum over all possible... Whoops, sorry, let me write that. So this is my system. It's going to evolve according to some energy operation. And so the input is going to be some wave function, psi n, for these n qubits. Okay. Computation is going to be evolve with some energy operator, which I've chosen to implement an algorithm. In the same way that the precise series of magnetic fields that we turn on in a classical computer, currents that we allow to flow in a classical computer, implement the algorithm we want to affect. We evolve with some energy operator, implementing an algorithm, we get some output wave function psi, again, for our n bits and quantum bits. This is a basic gig with the quantum computation. We're just replacing strings of binary numbers and functions evolution according to classical mechanics and Maxwell to other strings of numbers with superpositions of states, superpositions of strings, as it were, evolving according to the Schrödinger equation into, again, general superpositions. So how does this differ? What are the key differences from classical computer? So the key things are, first of all, the input and output are not definite values. They could in general be superpositions. They do not have to correspond to a definite state in the 1-0 basis. Right? These in general are superpositions of 0, 0, 0. 1, 0, 0. Okay. So the input and output are superpositions. Of the values we'll measure. Okay. Second, when we do measure, at the end of the day, the output, we get interference from the various different terms of the superposition. The different terms of the superposition will lead to interference effects, and so our output will be sensitive to that interference between different terms of the superposition. It may be that we're in some pure state, but it may be in general, more generally, we'll be in some superposition of the states we want to measure. So we're going to get interference. So, naively, this is a disaster because this means we get probabilistic outcomes. That sounds bad. And so this leads to the key difference in quantum, or the key move in quantum computation. Given that we're going to have interference, and given that those interference effects are going to affect the probabilities of various outcomes, what we're going to want is to tune or orchestrate the interference to get a definite outcome. We want to get the right out, the correct answer out, rather than just probably the correct answer out. Now, there's a slight variation of this. It's not obvious at the beginning how to do that. It's not even clear that you can. So I'm going to show you that you can. I'm going to show you an explicit algorithm that realizes this. But, okay, that's obviously going to be tricky. Here's something else you can do. If you can also focus on special problems. Focus on checkable problems. Okay, what do I mean by this? Imagine we have some algorithm that gives us an output, and that output is probably the right answer, but we're not sure. There's some quantum mechanical probability that this is the correct answer to our calculation. There's some probability that it's not. So, if the calculation was difficult, but it's easy to check whether you have the right answer, then that's great. Imagine it's 10% you get the right answer, but it's trivial to check. So, for example, factor the numbers, right? If you multiply the numbers, that's easy. You can check by concealing everything. So, for example, imagine I build a computer that is supposed to factor numbers. I almost said factor prime numbers. That would be boring. So, imagine I build a machine that factors numbers, right? And so, imagine its output is probabilistic. So, you say 15 and I say 3 times 5. You say 15, I say 5 times 3. You say 15, I say 7 times 2. At that point, you're like, well, which one's right? Well, you can check by multiplying, right? So, if you have a problem which is easy to check but hard to do, then probabilistic is already okay. And that's just as true classically as it is quantum mechanical. Those are basic moves. And so, the key thing for us is that when we have n quantum bits, we have these interference effects, and in particular, as discussed, as we started talking about last time, we get entanglement effects. And what we're going to discover is that the key to making a good quantum algorithm is going to be to tune the entanglement appropriately. So I'm going to have to define that for you in just a minute. Yeah. Sorry? The check, even here may not be. So the check, for example, could be, like, for example, imagine the process I just gave you. So the question is, what do you do if the checking process is probabilistic? Well, you need a classical computer to check if you have an easy checking algorithm. For example, multiplying numbers together. No, because, so the question then becomes, it doesn't have to be the point of using a quantum computer, you need a classical computer to check. And so here's the thing. If I ask you to factor a gigantic number, what do you have to do? You have to take all numbers up to its square root, and you have to multiply them together, and that takes forever, right? But if I tell you, to these two numbers, multiply to give you a third number, that's easy, right? So it gives a quantum computer for the hard part and a classical computer for the forward part, for the checking. And that's a special class of problems which are checkable. These all have fancy names in information theory. I'm not going to use the fancy names yet. Yeah, exactly. I mean that when we compute, so suppose I give you some output, and let's say the output is 0, 0 plus 1, 1. Right? What are you going to get if you measure the first bit? Well, you're either going to get 0 or 1, with one probability or another. Right? When we compute probabilities in general, when we have many terms in our superposition, we're going to get interference effects from different terms in superposition. Right? And those interference terms will tune the probabilities, so not just the naive probability score, the probability of that one thing, but you get the common interference. Norm squared 1, norm squared 2, and then the real part, twice the real part of the cross term. And that twice the real part of the cross term didn't exist classically. Quantum mechanically, it's important. I can change the final probability. That's what I mean by the interference effects. Okay, so let's make all this much more explicit. So far I'm just giving you philosophy, and you should be deeply suspicious of philosophy in physics class. So, again, to be explicit, a quantum bit, or qubit, is equal to a two-state system. And again, the substrate doesn't matter. I could be talking about spin on half systems, or I could be talking about, ropes on a cylinder mod with winding mod 2. I could be talking about all sorts of things, but it's some system with two quantum states, 0 and 1. I want to emphasize this is not going to be on the final, so this is for your moral well-being. Okay. So a quantum bit is a two-state system. We have these two states which I'll call 0 and 1. And the general state, the general wave function, is psi is equal to alpha 0 plus beta 1. Okay? And the probability, what this means is the probability that I measure 0 is equal to 1 alpha squared, etc. Okay? Now, again, many systems can use many different substrates. This is what we mean by qubit. So that's one qubit. The much more interesting system is two qubits. So let's study two qubits.
I don't know if you can hear the cat right now. I'm cat sitting, and this cat is a little meowing.
So in the case of two qubits, what's the general state? Well, the general state is going to be, well, the first particle could be 0, and the second particle could also be 0. Or we could have the first particle 0 and the second particle 1, with some coefficient, plus beta, plus gamma 1, 0, plus delta 0, 1. Okay? So this is just a general solution. They might rate this by looking at these identical or these non-identical spins. Right? But here's the thing. I've got a spin here, it's in a box. I've got another spin here, it's in a box. I've got another qubit over here, it's in a box. So they're distinguishable because they're in different places in the laboratory. So these are distinguishable particles. Right? The particle in this box is either up or down. Okay. So these are distinguishable. I don't have to worry about symmetrization. Goes on here for statistics or any of that. They're distinguishable. And we need normalization. So norm alpha squared plus delta is equal to 1. And what does this mean? Well, what this means is that, for example, the probability of the first particle, which I'll call A, is equal to 0, is equal to, well, it's all, we show all the possible ways we do that. We have norm alpha squared plus norm beta squared. But these guys are, whoops. This is 1, 1. Thank you. And if we're more specific, probably the first qubit is 0, and the second qubit is 1, is equal to 1, 0, 1. That's this guy is norm beta squared. Okay? What do I mean by two qubits? But this immediately leads to a funny thing. There are two kinds of states that a pair of qubits can be in. A very special set of states, which are called separable states. And these are special. And these states correspond to the full system being in the state where the first particle is in one state and the second particle is in the second state. Okay. So for example, this could be e.g. The state 1 over root 2 up plus 0 plus 1 for the first particle, and the second particle will be in the state 1 over root 2 0 minus 1. Oops. It's not these are oh, let's just call these general coefficients. A plus B and C plus D. So what is this equal to? Well, this is of the form, well, there's going to be a term that's 0, 0, and that's AC, plus the term that's 0, 1, and that's AD, with a minus AD, plus the term that's 1, 0, and that's BC, and plus the term, minus the term that's 1, 1, and that's BD. Okay? But this is clearly not generic, because it implies relationships amongst the alpha, beta, delta, gamma, apart from just normalizability. Ever see that? So it's a pretty non-trivial thing that you can write a thing as the first particle is in one state, and the second particle is in the second state. And here's physically what that means. Physically what that means is that if you're in a state like this, and I ask you, what's the probability that I measure the first particle to be 0? Do I need to know anything about the state of B? No. The relative, if I want to know the probability of the first particle is 0, I just take norm A squared, because I'm going to get plus norm C squared plus norm D squared. And if I want to know whether the first particle is going to be B, okay, so that's fine. So imagine, the probability of the first particle being up or down is independent of any information about the second particle, right? There's another thing that's important. Suppose I tell you, I measure the first particle is in state 0. Okay, cool. What is the state subsequent to that measurement? So if we measure A is equal to 0, what is the state subsequent? Psi is equal to, well, that's 0, and we know we've lost this, so this particle is now, this particular subsystem, this particular qubit has been collapsed to state 0, so we have 0 times C0 minus B1 for the second particle. Have we learned anything about the state of the second particle? Have we learned anything about the state of the second particle? Absolutely not. Right? Beforehand, what was the probability that the second particle is 0? Norm T squared. And the second particle 1? Norm D squared. Now what's the problem? Same, norm C squared, norm D squared. So we have a separable system measuring one qubit tells you nothing about the other qubit. Cool. On the other hand, consider a state which is not separable. So the generic states are not separable. And we give an example of a state which is not separable. Which one do everyone think? Yeah, what the hell? Psi is 1 over 2, 0, 0, plus 1, 1. Can this be written as the product of the first particle in one state, the second particle in the other? No, because there would have to be cross terms which don't exist here. Right? Just compare this to that form. So we have that the coefficient of 0, 0 is AC, and so A and C must both be non-zero, and the coefficient of 1, 1 is BD, so the coefficient BD must be both of those must be non-zero, so A, C, and BD are all non-zero, then these terms have to exist in order for it to be separable. Yeah? Because A and D can vanish and B and C can vanish, and these orthogonal states are independent. So this is not a separable state. We call these states entangled. And it's funny because entangled BD? Yeah, I think there's an E in there. Okay, that's better. Look, I'm not a professor of spelling. So we call these states, it's a little bit funny to call these, to give these a special name and call them entangled, because the generic state is entangled, right? It's sort of like calling mice, calling mice mice and calling all the other mammals non-mice, right? Oh, look, well, that was a bad example. Look at my circuit. Harkening back to an earlier lecture. So in any case, we give these a special name. The reason we give them a special name is that these separable states do more or less what you expect classically. There's no strange correlation between the state of one and the state of the other. They're independent quantities, but when you have a generic state, something funny happens. They're entangled. And here's the funny thing that happens. Suppose, given the state, what's the probability that I measure the first particle to be up or to be 0? 1/2. What's the probability that I measure the first particle to be 1? 1/2. Okay. So before doing any measurements, the first particle is equally likely to be either 0 or 1. But suppose I measure the second particle to be up. Okay. Then the probability that I measure the first particle is 0 is equal to 0, and the probability that the first particle is 1 is equal to 1, because I collapse onto this term in the wave function. So measuring the second qubit alters the probability distribution for the first qubit. These guys aren't independent. They are correlated in a way that you studied on the problem set. They are correlated. They're in a correlated state. We call this correlation entanglement. And here's the thing that's most spooky about this, and we'll come back to this in a few minutes, but I didn't tell you anything about the geometry of this setup. But in fact, when I was thinking of that measurement, I built the 2 little qubits in my lab, and I took one, and I sent it to France, and I took the other, because France, and I took the other one, and I sent it to the planet Zorg, right? And so off of the planet Zorg is some poor experimentalist huddling in the cold, and our French experimentalist makes a measurement, altering the probability distribution instantaneously on Zorg. That should make you a little worried. That sounds a little crazy. We'll come back to why that is or isn't crazy, and the EPR analysis, which sort of puts flesh on it, sounds crazy in a little bit. But for let me just emphasize that while the generic state is entangled, the generic state is also different than what your classical intuition would expect. There are correlations between the particles. So this is something that happens with quantum mechanical particles that doesn't happen with classical particles. And that means it's something that can be used in a quantum computer that can't be used in a classical computer. So let's see what using entanglement gives us for computation. So let's come back to the quantum computing problem. And how do we compute with qubit? So how do we compute? Okay, so again, as usual, the way we take our input to our output is we build a machine that implements an algorithm of our choice by arranging the physical evolution of the system over time. So that means picking an electric field. Or sorry, an energy operator, an electric field, good lord. So it means picking an energy operator. Okay, so computing is trading evolution with our chosen energy operator. So for example, I want to build for you now a couple of basic circuit elements that you might want to use in a quantum computer. So example 1. First example is I want to build a NOT gate. And what NOT means is it takes the state 0 and it gives me 1, and it takes the state 1 and it gives me 0. Okay? This is what NOT does. So how do I build a NOT gate? Well, I can realize this in a nice way. Do you want to see that? Yeah, good. So if I realize 0 as 1, 0 and 1 as 0, 1 from last lecture, then 1, 0, oh, sorry, 0, 1, 0, 1, 2, 1, 0. So we need an operator, we need time evolution to affect multiplication by an operator that takes this vector, this vector, this vector, this vector. But we know what that unitary operation is. That unitary operation, which I'll call NOT, must be equal to 0, 1, 1, 0. And this operation takes this guy to this guy, and takes this guy to this guy. Yeah? But I can write this as, I like this. I can write this as, shoot this phase, minus sign, e to the I pi over 2, 0, 1, 1, 0. I mean, you can't stop, right? So this expanded out, as we've done before, expanding this out, gives me, with the exponential, 1 plus the thing, and then all the other terms. This becomes minus I times cosine of pi over 2 times the identity, 2 identity, plus I sine of pi over 2 times 0, 1, 1, 0. Okay, but what's cosine of pi over 2? Yeah, 0. Come on, so cosine pi over 2 is 0. Sine pi upon 2 is 1, because I times minus I, that's 1 times 0, 1, 1, 0. Pretty solid. But what is this? Well, this is the form, this is Schrödinger evolution with a magnetic field, and this is just the unitary transformation for a magnetic field well, okay, we can say this. This is the x Pauli matrix from last time. So this is like Sx, unitary transformation for a magnetic field in the x direction for some time t. For time t times the frequency omega, which is given by u b upon 2, is equal to pi upon 2. Okay, just like before, but for a slightly different one. Slightly different magnetic field. So my point here is we can take a magnetic field that does this. We turn on a magnetic field with a known entity with no amount of time. We turn a magnetic field in the x direction, and it takes 0 to 1, 1 to 0. Remember that? So here is a substrate, an actual physical system that affects this particular evolution. I can build a knot. Crucial thing is I can build a knot gate. And I'll represent that knot with some unitary transformation use of knot. So that's a useful one. It's not the most useful game because gate. If you only ever impose logical knots, you just get over angry because you don't actually get anything done. So second example. Let that be a lesson to you, Congress. So the second example, if we turn on the magnetic field in the y direction for a time t, for a particular time t, what we find is that 0 goes to 1 over root 2, 0 plus 1. Okay? And 1 goes to 1 over root 2, 0 minus 1. Okay? And this should be familiar. This is the up x state, this is the down x state, just as we talked about before. So we turn on some B field and we get this. So this operation is called, it has a name because it's going to turn out to be very useful for us. It's taking a system that's definitely in state 0, for sure, right? And it puts us in a superposition 0, 1. It's a definite superposition, so it's not like we don't know what happened, but it's a superposition and you've lost certainty that you'll measure up in the z direction. You gain certainty that you'll measure up in the x direction. But if we do our measurements in z, we've just taken ourselves from definite to superposition. Cool? So that's useful because we know that something a quantum computer that can do that a classical computer can't do, something a quantum computer can take advantage of that a classical computer can't take advantage of, is this process of putting things in superposition. So here we've got an operation that puts things in superpositions, and I'll call this Hadamard. I don't know the history of why that's called Hadamard. Presumably there's some guy with the last name Hadamard. Anyway, the Hadamard does this, and as a matrix, it's represented as 1 over root 2 times 1, 1, 1 minus 1. Okay. And there's a last one, which is going to be useful for me, which is called, and this is represented in the following way. Well, don't worry about it. Another one is called C naught, control knot. Control knot does a really cool thing. It takes 0, 0, and 0, 1, and 1, 0, and 1, 1. What it does is it says, I'm going to apply a knot to the second qubit if and only if the first qubit is a 1. So this takes me to 0, 0 goes to, well, do I perform a knot on this bit? No. So 0, 0. Do I perform the knot on this bit? No. 0, 1. Now I do perform a knot on 0, so I get 1, 1. And 1, 1, I perform a knot on this bit, which gives me 1, 0. Okay. So this is called a controlled knot. It's a very useful thing. I mean, I'm going to represent this in the following way. I should represent all of these. So this knot gate first, I take the initial bit, and it's in some state, and then I impose U knot, and it gives me an out state. Similarly with Hadamard, I take an initial state in, and I apply U Hadamard, and I get U out. And for control knot, I now have 2 qubits. And I take the 2 qubits, and I do a control knot, which is represented this one, which says do a knot on this guy, controlled by this first bit. Okay? And so this acts as U C knot. Okay. And the key thing here is that while it's
how does that work?
It's always possible to find a physical representation of some particular unitary transformation. At the end of the day, all we're going to need is some truth tables. At the end of the day, all we need is the logic that's being affected. And so the details of the substrate can be abstracted away. Okay. So what can we do with this? Right. So what can we do? Before we actually talk about what we can do with it, let's briefly talk about what we can't do with it. So what are things you can't do with these sorts of operations? What can you do? And to me, this is only more surprising. So here's the least surprising thing. Remember that what we're doing here is going to be involving a system form of Schrödinger illusion. And Schrödinger illusion is linear. It respects superpositions. It's unitary. It preserves probability. And it's, well, let's just focus on that. Linear, unitary. It has lots of other properties. Universal invariant, unless you're trying to make a field. But in theory, it's linear and unitary. And those facts are going to constrain powerfully the kinds of operations we can effect on a quantum system. So in particular, when we look at just 2 qubits, there's a beautiful theorem that says there's no cloning. And here's what that means. The no cloning theorem, which is pretty highfalutin for what it really is the following. Suppose we have a system which is input x, y. And I want to build a machine that says, look, I've got this first qubit in the state x, and what I want to do is I want to make a copy. I want to make another quantum system that's in exactly the same state as whatever x is. So you have a system where the first bit's in state x, the second qubit's in state y. And I want to make a copy of x. And y is just the, I mean, who cares what's in it? Okay? So I want this to go to x, okay, for all y. So regardless of what data was in here, I'm going to overwrite that data and rewrite it, or that data, and rewrite it with x. Can you do this? No. Right. Why? Actually, it would violate linearity and also unitarity, indeed. So, to see that quickly, so it's easiest to see the unitary, I think, well, if I but for unitarity, when you take a linear combination of these guys, that are where the two states y are orthogonal, you take the norm squares, so you normalize it to 1. That linear combination, each one goes to xx, but where the coefficient is the sum of those two terms. So we have, for example, x, z, alpha x z plus beta x y goes to alpha plus beta xx. And that's really bad, because if these x, z, and y are orthogonal, then normalization is alpha squared beta squared is 1. But xx, the normalization is alpha plus beta quantity squared is 1. And in general, that's not true. In fact, this could be 0. So this violates linearity and unitarity rather badly. So you can't clone. This is really disturbing. That means if you have a quantum state and you want to make a copy of it, you can't. You can't ever make a copy of your quantum system. One copy, one chance. That's it. No cut and paste. So as you can imagine, that pretty powerfully constrains things you can do. So a related thing here is that there's no forgetting. Quantum evolution is, unlike an elephant, it is highly, it has very, well, it's like an elephant. It remembers very well. It never forgets anything. And you can see that from this. This would be an example of forgetting. You forgot what was in state y. You can never do that. Okay. So I think this is a challenge to you to prove this. Show. It's a simple extension of the same logic. So what can you do? What you can do is you can entangle two qubits. And that's really the juice of everything. You can. Oops, you can. Okay. Let me show you entanglement. Good, no E. So you can entangle, here's how you do it. Let's take the state 0, 0. So we have two qubits. The first one's in the state 0, the second one's in the state 0. And now I'm going to do the following set of operations here. I'm first going to impose a Hadamard operation on the first qubit and nothing on the second. And then I'm going to apply a controlled knot. Okay. I'm going to see what I get out. So the initial state is 0, 0. Right? I'll write this as 0, 0. After I Hadamard, the state is, well, the first bit is no more than 0. Hadamard on 0 gives me 0 plus 1. So this is now the state 1 upon root 2. 0 plus 1 times 1, or sorry, times 0. Okay. Also known as 1 over root 2. 0, 0 plus 1, 0. And is this a separable state? Yes, there it is separated. And now I'm going to perform a controlled knot. And what the controlled knot does is it switches the second bit if the first bit is a 1. So what is the state after we've done this? The state after we've done this is, well, from the first term, 1 upon root 2, from the first term, 0, 0, what happens is that when we control knot, well, we knot this if this is 1. So not 1, so we don't knot, we leave it 1. The second term, 1, 0, plus, well, we flip this if this is 1 and not if it's not. This is 1, we flip it, we get 1, 1. And now this is the predictable entangled state. That I think I just erased. This is our entangled state, it's not separable. If I measure the first one, I know what the state of the second one is, which is to say it's entangled. Cool? So by performing this series of operations, which is nothing other than a series of magnetic fields, which I'm going to pose to the system, I've taken a state with initial condition 0, 0 and put it into an entangled state, 0, 0 plus 1, 1. Cool? And that's all we need for the first basic algorithm of quantum computation. So this idea that quantum computers might be able to do things faster than classical computers floated around for a while. It took a while for people to make that sharp. And David Deutsch, who is a very entertaining, bombastic speaker, and he wrote, I guess, several now, pretty entertaining books on the topic. And he sounds crazy. You listen to the guy talk, and he sounds nuts. He sounds like, he's just way out there. He's just, God, as a theorist, you listen to him, oh, just slow down everybody, right? And so for a long time, I thought, God, I'm telling you this sort of public persona. I thought, yeah, I think it's a little bit crazy. I'm not exactly sure. And this is why everyone thinks he's such a damn genius, because this is beautiful. So here's, I don't know how he came up with this, but he's clever. So here's what's now called the Deutsch, the version of one bit version of the Deutsch Joseph algorithm. So there was the first algorithm by Deutsch, wasn't quite what it was supposed to do. There was some proof, getting with Joseph and the n particle version, and everything was awesome. But here's the Deutsch Joseph algorithm. And what it is, it's a series of rules for how to make a quantum entangled system so as to affect the calculation you wanted to calculate. So you have to grant, to begin, you have to let me pose a problem to solve that can be solved in this fashion. And this problem is going to sound a little contrived. And in fact, it's wildly contrived. It was contrived so it could be solved in this fashion, but it's actually it's one that pre-exists the algorithm itself, so it's not quite as ridiculous. So here's the problem. So the secret of the problem is that someone has a function f of x. So let's say Matt knows a function f of x. Now the thing is, it's extremely expensive to evaluate this function f of x. Right? So the way you evaluate involves putting 20 kilometers in superposition states with each other. You have to run a whole experiment, and it costs a lot of money to run. So he charges $1 million in order to. Thank you. You're kind of not quite old enough. So he knows the function f of x. He charges $1 million in order to evaluate the function. You say, hey Matt, well look, I know this is a function. I should tell you, f is a function that takes a single bit 0 or 1 to another single bit 0 or 1. So it sounds like how hard can this possibly be? But in fact, it's a very hard function to evaluate. So you say, hey Matt, what's f of 0? He's like, give me $1 million. Give me $1 million. He's like, what? I'm like, 10 that. Also one of me. Okay. So and now here's the question. So this is now the problem. The problem is this: is f of 0 equal to f of 1 or not? Okay. Is f of 0, so f of 0 is either 0 or 1, f of 1 is either 0 or 1, are they equal to each other? So this is easy, right? Classically, this is stupid. You've calculated the function f twice. You evaluate f of 0, you get a number. You evaluate f1, you get a number. You look at your piece of paper, you say it's either the same or different, right? How much does that cost you? $2 million. Better have good funding. So this is an expensive, and here's what Deutsch and Jose have to say, and this is really Deutsch at the beginning. It's really quite spectacular. Deutsch says, actually, I tell you what, give me $1.5 million, and I'll do the computation and give you the answer. At which point you think, like I did previously, the guy's clearly raving. But in fact, he's going to make a profit. And here's how he's going to do it. He's going to build not a classical computer, but a quantum computer using quantum interference and entanglement to do this calculation with one evaluation. Here's how it's going to work. So the first thing we have to do is a preview, setup. In order to do this calculation, you need two things. First off, you need Matt to be able to to evaluate his function in a way that respects quantum mechanics. Okay? So in particular, Matt had better be able to do his experiment if I give him a superposition. So he better be able to affect the calculation in a quantum mechanical way, the same way that he implemented a not quantum mechanically or a controlled not quantum mechanically that had more, with some set of magnetic fields. He must be able to implement it quantum mechanically. Otherwise, it's not an interesting function. And let me just point out that any function you can think of can be implemented quantum mechanically because you are quantum mechanics. Okay? You're just not elegant implementation, no offense. You're just not an elegant implementation of the quantum mechanical computation. So what I want, so setup is Matt needs to be able to give me. Matt provides a unitary transformation, unitary operation, use of f, that takes two qubits, x and y. Okay, 2, x, and f of x plus y. Where what this means, f of x plus y, is addition 1, is 2. So what this says is if y is 0, then this gives me f of x plus 0. 0, that's 0 plus 0, so it gives me 0. If f of x is 1, it's going to be 1 plus 0, that's 1. And then if y is 1, then this gives me, if f of x is 0, this gives me 1 plus 1, which is 0, and if f of x is 0, this gives me 0 plus 1, which is 1. Everybody that? Okay. Yeah.
So we have a question about having that calculation actually how would that actually go to calculate
You what quantum mechanics is only in the practical description of the Is inescapable? Yeah, this is an interesting question. So it's tempting to think that this is a philosophical question, but it turns out not to be in a way that will be sharp in about 10 minutes with Bell's inequality. But a good answer, a complete answer to that question remains open, and I think it probably always will. But can we rephrase the question so that tell me if this is an accurate state? Look, at the end of the day, what we're doing is we're going to develop a model where quantum mechanical calculation does something in particular. And it may or may not be a good model of the real world. And in particular, whatever the actual thing, the actual system that we're studying does, may or may not be well described by that quantum mechanical model. So we check whether or not it is. And is that more or less the question? Yeah, it's a hard thing to make. So the problem is, all we can ever do is say that our model is a good model or a bad model. On the other hand, we can do the following. This is a really neat thing. You might say, look, underlying quantum mechanics is going to be something more fundamental that's going to lead to slightly different results in exactly the sort of situations where we're going to care about quantum computation with large numbers of bits. And if you tell me just a little tiny bit about what properties that underlying description will have, that becomes an empirical question. So, for example, if you say, look, I suspect that underlying the quantum mechanical probabilities is some classical probability distribution over a hidden variable that you have not actually measured. And what we're going to find out is that we can rule that out experimentally. Just that extra little assumption that there's an underlying hidden variable secret probability distribution on some variable we just haven't observed yet. That is enough information about the system to rule out that model amazingly. So I think we'll never have a full answer to your question, but all we can do is work and see how well our model fits. And so far, nothing's ever disagreed with quantum mechanical description. Let me hold off on questions just a second. But it's a good and interesting question. It's a hard one to deal with. by which I mean it's an open question. So Matt provides for us an operator that allows us to calculate f of x. Now, remember, you might have said, well, look, why not just take x? Why not have Matt build a machine that takes x and gives you f of x? Could you have done that? Well, it's not exactly no cloning, but let me leave this to you as a fun thing to think about. Why do we need this carrier bit as well? Okay. So there's our setup. Matt provides this function for us here. And here's the algorithm. So the algorithm. And it's a series of steps. One by one we do them. We perform these operations on our qubit. So here's what Deutsch says. Deutsch says start input a state psi is equal to 0, 1. First qubit is 0 in the state 0. The second qubit is in the state 1 for sure. We implement that with our boxes or however we want to implement it. So we find ourselves in a definite state. Hard, soft. We take a hard box and we take a soft box. We pull out a hard one and a soft one. 1. Add more each. Add one on both bits. Both bits. Okay. So what does this take us to? It takes us to psi is equal to, well, the 0 goes to 1 over root 2 times 0 plus 1. Did I erase head more? No, good. There's head more. So it does this, does this. So it takes the first one to 0 plus 1, and it takes the second one to 1 over root 2. 0 minus 1. Cool. So this function is very interesting. All we've done is we've taken it from one superposition to a different superposition. And it doesn't have anything to do with f. In fact, we haven't measured f. 2. Apply f. So we apply our operation use of f. And this takes us to, well, this is a sort of entertaining one. If we take this 1 over root 2, or something like this, in a set of these before, this is 1/2, 0 times 0 times 0 minus 1. Plus 1 times 0 minus 1. Okay. And the reason I'm doing that is we're going to apply UF, and UF, our function f, uses that first bit as a control bit for the second. So here's the control bit for the second. So we apply UF, and this gives us 1/2. I'm going to actually do this on the next board, because it's going to be... So this gives us 1/2. 0. So that first one, this is going to take this and give it 0 plus f of 0 and 1 plus f of 0. So times f of 0 plus 0 minus f of 0 times plus 1 plus, for the 1, this is going to be times f of 1 now plus 0 minus f of 1 plus 1. Okay? Now here's a crucial step. This is equal to, and want to note the following. Look at this particular guy. Okay. So for that particular guy, suppose f of 0 is 1. Or sorry, is 0. If f of 0 is 0, then this is 0 plus 0, which is 0. So f of 0 equals 0. Then this gives me 0, and this gives me 0 plus 1, which is 1. 0 minus 1. On the other hand, if f of 0 is equal to 1, then we get 1 plus 0, which is 1.
Just going to call this A, B, D.
And here we get 1 plus 1, which is 0, minus 0. Which is equal to minus 0 minus 1. Yeah? So I can write this as minus 1 to the f of 0 times 0 minus 1.
Recall that? This is just a little exercise in binary arithmetic.
So I can write this first term. This is 1/2. Minus 1 to the f of 0. 0 times 0 minus 1. Okay, so that's from the first one. And exactly the same logic is going to apply to the second, but now f of 1 instead of f of 0. So plus minus 1 to the f of 1 times 1 times 0 minus 1. Now I want to point something out to you. If f of 0 is equal to f of 1, then what's true of f of 0 plus f of 1? Well, if they're the same, exactly, then either it's 0 plus 0, in which case we get 0, or it's 1 plus 1, in which case we get 0. So this is 0 if it's the same, and 1 if it's not. Okay, so we could either know them both, or we can measure f of 0 plus f of 1. So notice what happens here. This is equal to 1/2, and now I'm just going to pull out a factor of f of 0, minus 1 to the f of 0, times, well, both of these terms have a 0 minus 1 on the second bit, so the second qubit is in the state 0 minus 1, right? Everyone recall that? So this is equal to, for the first qubit, 0 plus 1 times minus 1 to the f of 0, but I pulled out to square it, plus f of 1 times 0 minus 1. And here's the quantity we wanted to measure. If this is 0, then they're even. Then they're the same. If it's 1, then they're not the same. So now at this point, we just forget 3, forget about the second qubit. Oh Lord. Forget about the second qubit, and we get the state, so forget about the second qubit just does this. Just focus on this guy. And now if f of 0 plus f of 1 is 1, or sorry, is 0, so that they're the same, this is 0, minus 1 to the 0 is 0, so we get 0 plus 1. So same, then our state is 0 plus 1. And if they're different, then we get the state 0 plus, or sorry, 0 minus 1. Everybody agree with that? So if they're the same, we get 0 plus 1, we get different, we get 0 minus 1. It still doesn't work for us, because if we measure what's the probability we get 0 here? 1/2. The probability we get 1 is 1/2. It's similar if we measure here, 0, 1/2, 1, 1/2. On the other hand, here to us, because then we get by Hadamard. So why don't we take these from these states to these by doing the inverse of the Hadamard, which it turns out is Hadamard itself. So 4, Hadamard first bit, add first bit, and we get the output is the state sign is equal to 1/2 1 plus minus 1 to the f0 plus f1 0 1/2, 1 minus 1 to the f0 plus f1, 1. And now if f0 plus if f0 and f1 are the same, this is a 0, we get 1 plus 1, we get just 0, and this is 0, because this is 1, this is 1, these are subtracting to 0. So the same, you get this state 0, properly normalized. If they're not the same, you get this state 1, properly normalized. Now if we measure 0, we know they're the same. If we measure 1, we know they're different. And so with absolute certainty, now 5, measure the first qubit. And we get 0 implies the same, and 1 implies different. And we did all of this with a single evaluation of our function f right here. Right? This is where we applied our function evaluation. We applied the function evaluation once, and we deterministically get the result, whether they're the same or different. So with one call to math, to my oracle, with one call to math, which cost me $1 million, we get the answer to whether it's the same or different. And that's a factor of 2 faster than the best classical algorithm. But that's not so satisfying. This was supposed to be exponentially better. And so that's where Jose comes in. And together with Deutsch and Jose show the following. That there's an exactly analogous problem for n qubits. Wow. There's an exactly analogous problem for n qubits. Deutsch-Jose problem. Okay. And now how many different strings of integers could you put in? They're now 2 to the n possible states. And if you want to know whether f is the same for all of them, the worst case scenario is you measure that you evaluate f on the first possible combination, 0, 0, 0, 0, and you get some number. You measure f on 0, 0, 0, 0, 0, 1, and you get the same number. You just keep doing that forever. And you still don't know if they're all the same until you get to the very last one. Right? So it's 2 to the n, it's order 2 to the n is worst case scenario. But typical scales are of order 2 to the n. So classically, it takes an enormous number of observations. But the quantum Deutsch-Jose algorithm, so that was n-bit Deutsch-Jose, and then the n-qubit Deutsch-Jose problem, 1 quantum operation. And you get a deterministic result. And all of this, 1, right? You evaluate it once and no, you solve the problem. So instead of 2 to the n operations, it takes a single 1. And now for a large number of n bits, for example, for large integers, dealing with very large numbers, this is dramatically exponentially more efficient than the classical algorithm. So this is the basic. At this point, people start really seriously thinking about quantum computation, whether you could get it to work, and how much juice you could get out of actually building such a quantum computer. This is developed in a whole theory in the whole field of the theory of computation. The thing I want to emphasize is that the crucial move is observing that in quantum mechanics you can entangle degrees of freedom. The crucial move is observing that you can entangle degrees of freedom quantum mechanically, and that's what gave us all of the nice effects. We have these interference effects. These interference effects lead to the deterministic outcome being correlated with the result of the computation. The interference is crucial, and this brings us to the last point, which is exactly what's so troubling about entanglement. And so here is where you are. And Pythagoras and Rosen say the following. They say, look, there are 2 things that are deeply upsetting about this entanglement story. The first, let me just give you a precise experiment. They say, let me give you a precise experiment that embodies all of your discipline. Suppose I take 2 of these qubits, and I put the first one, and I put the 2 qubits in the entanglement state, up, plus down, down. Okay, let's normalize this with 1 upon root 2. So there's our state. And then we take the first qubit, so there's our 2 bits, and we take the first qubit and we send it some far away, and someone named Alice is sitting here and is holding onto that bit. And we take the second one and we take it far away, and someone named Bob, conventionally, is sitting here and holds the second bit. Now, given this initial configuration, what is the probability that Alice will measure the spin to be up? Her spin to be half, right? And then half down. Similarly, Bob half up and down. Once Alice has measured the state to be up, right, immediately she knows something about Bob's spin. Bob's state will be up, because I chose this one. I could have chosen the other one, which is the more popular EP. Okay. So Bob's will also be up. Now, if you look at the list, if you do this over and over and over again, their list is just some random list of ups and downs, but they're exactly correlated amongst each other. So at this point, EP are really upset because they say, look, there are 2 possibilities. Either there was an answer to the question all the way along of whether Alice's was up and Bob's was up, or Alice's was down and Bob's was down, or there's some deep non-locality in the universe such that a distant measurement, causally disconnected, can have an influence on Bob's state such that they're correlated. This may seem random, but it's certainly not random because it's correlated with Alice, even though Alice is wildly disconnected, distant observer. Nothing could have traveled across that time, across that distance in the time it took to do the measurement. So there are sort of 3 responses you can take to this. The first response is, look, there isn't a problem here. It's just saying that quantum mechanics is insufficient. There's secretly a hidden variable, a variable you haven't observed yet, a property of an electron that determines whether it's going to be up or down early on. And the fact that it looks probabilistic just means that there's some classical dynamics for this hidden variable that effectively is probabilistic, like a particle moving in a fluid, like dust pollen grains in a fluid. It just moves around randomly. So when it just looks random, it's not actually random. And that's because there's an underlying classical mechanism in the probability distribution. The second version is a quantum mechanical version. The second interpretation is to say, look, this is a lookup setting, and I grant you that a lookup setting, but I'm a quantum mechanic, and quantum mechanics works like a chain, and I'm not about to throw it out and say that there's some secret hidden variables. It just works. So just give up on your naive notions of locality, let it go, and just do the quantum mechanical calculation. Practicing physicists look at this and just yawn, right? If you're practicing physics, you just forget it. Like, it obviously works, so there's no more competition to be had. So meanwhile, there's a second version of this, which is slightly more mystery. Suppose Alice measures up, and this is all in the z direction. Suppose Alice measures up in the z direction. She must know that Bob's particle is up in the z direction. But simultaneously, Bob could measure spin in the x direction, and determine that his spin is up in the x direction as well. At that point, the EPR say, look, we've measured, empirically, we've measured that the particle is both up in the z direction and up in the x direction. It's just we did that measurement using data. But at the beginning of the day, at the very beginning, oh shoot, hey, that's not what I want. So at the very beginning of the day, means that SX and SD don't commute. So you can't have a state with definite SX and definite SD. You cannot possibly, it doesn't mean anything to say so. Einstein wants to say that this is because quantum mechanics is great but incomplete. The rest of us want to say that no, it's not. But that sounds like that's like a philosophical question. That's what it was treated for a very long time until you come along to Bell. And Bell made a beautiful observation. Bell said, look, telling me that there's an underlying classical description, telling me that there's an underlying probabilistic classical description tells me enough to make this an empirical question, because it's saying that the random statistics for Bob and Alice are correlated by a classical dynamics rather than independent. So here's Bell's version. So remember at the very beginning, we talked about Bell's experiment. We said, consider three binary properties A, B, and C. The number that some set that are A and not B, plus the number that are B, but not C, is always greater than or equal. To the number that are A but not C. And the way we proved this was just by noting that if these are classical deterministic binary properties, then A not B means A not B and C, or A not B and not C. And ditto for each of these other guys. And we ended up with an expression which was number that are A, so using that logic leads to number that are A, not B, and C, plus the number that are not A, B, and not C is greater than or equal to 0. And that's clearly true. You can't have a number of elements be negative. So this is trivially true quantum mechanically. But now here's the experiment I want to do. I want to do actually the EPR experiment. And here's the experiment I want to run. Alice is going to measure up or down at 0, and Bob is going to measure up or down at theta. Alice is then going to measure up and down at theta, and Bob is going to measure up and down at 2 theta. And the third experiment is going to be Alice is going to measure up and down at 0, and Bob is going to measure up and down at 2 theta. So A is up or down at up at 0, B is up at theta, B is up at theta. And this is going to be down at theta, not B is down at theta. B is going to be up at theta, and C is going to be down at 2 theta. And A again up at 0, and not C is down at 2 theta. So we can rephrase this as the probability that, given that we are up at 0, what is the probability that we are subsequently down at theta? Plus the probability that we are up at theta, and what is the probability that we are up at theta and subsequently down at 2 theta? And then the probability that we are up at 0 and down at 2 theta using an EPR measurement where one is performed by Alice and the other is performed by Bob. Exactly as EPR wanted. And we computed this last time. In fact, I just erased, because I'm excited about this. I just erased the wave function that we needed, the state we needed. And the state that we needed was that if we are down at the angle theta, then this is equal to cosine of theta upon 2 down at 0 plus I sine theta upon 2 up at 0. And this is enough. This is a question. What's the probability that given that we're down at the angle theta, we're up at the angle 0? Well, if we're down at theta, the probability that we're up at 0, the coefficient is I sine theta upon 2. The probability is the 1/4 convention coefficient, so the probability is sine squared of theta upon 2. Similarly, the probability that we're up at theta and down at 2 theta, well, by rotation by theta, this gives me exactly the same thing. So it's again going to be sine squared theta upon 2. Probably we're up at 0 and down at 2 theta, well, just stick in a factor of 2 for theta everywhere. And that gives me sine squared of theta. Now I ask you, is the left-hand side always greater than or equal to the right-hand side? And this is easy to check. Let's do this for very small theta. For very small theta, sine squared theta. So for small theta, what's less than 1? Sine theta squared is theta upon 2, the angle squared, which is equal to theta squared upon 4. And the next one is the same thing, plus theta upon 2 squared, which is equal to theta squared upon 4, theta squared upon 4, so it's theta squared upon 2. And the right-hand side is sine squared theta, which is theta squared. And is theta squared upon 2 greater than or equal to theta? Certainly not. So quantum mechanics predicts that if we do the EPR experiment using these observables repeatedly and build up statistics, what we will find is an explicit violation of the Bell inequality. And what that would represent if it were actually true, if we actually observed it, would be a conclusive empirical proof that there are no classical definite configurations underlying the probability of quantum mechanical events. It would say that it's impossible to build a classical theory with hidden variables that are randomly distributed, such that you reproduce the predictions of quantum mechanics. We see already that it doesn't agree with classical or with quantum mechanics. The question is, does it agree with the real world? So someone has to build this experiment and check. And this was done by Alain Aspect. And it violates Bell's inequality. There is no classical description underlying quantum mechanics. The universe around you is inescapably probabilistic. It evolves in a deterministic fashion through Schrödinger evolution. And when we measure things, we measure results with probabilities. And those probabilities cannot be explained through some underlying classical dynamics. If there's something else underlying quantum mechanics, whatever else we know about it, is not classical. And this property of probabilistic evolution, or probabilistic measurement, is an inescapable, empirically verified property of the reality around us. And that's quantum mechanics. Thanks, guys.
All right. And that is the last lecture. So let me just switch over here. I'm going to switch over to my camera here. So yeah, so I've got about a half hour left, but we finished all the lectures, or I finished all the lectures, I guess, which is good to experience. And it's nice to see some of the ideas from the beginning of the class getting kind of their final resolution, because the beginning of the class, if you go back to those things I talked about a little bit, they just point out all these crazy experiments that if you do them, it just violates your intuition about how things can work. And then we've been through this whole process of learning the math and understanding why, if you get familiar with that math, why this craziness would be exactly what you would expect. Why, for instance, you know, all these experiments that have the color box and the hard box, and if you send things through and you get it through one direction, and then you know, put it through two hardness boxes, if it's hard through again, you'll get 100% hard at the end. But if you put a color box in the middle, it suddenly switches to being 50-50 again. And so there's a lot of really interesting intuitions about this. Now, for me, my job of learning this, even though I finished the lectures, is really this is just a beginning part. One of my goals was to try to finish all the lectures by the halfway point, so I would be able to see the whole span of the course and then use that to invest time in working on things. So we've got 5 more problem sets that are provided by this class. And I also have some problems in this introduction to quantum physics, which I can work through. There might be some from the other classes, other sessions both on MIT's OpenCourseWare and on Stellar. And so I'm going to be spending the next, better part of a little over 2 weeks. Well, let me just look at the calendar so I can confirm. So it's April 11th right now. So we have spent a grand total of, this is day 9, and there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's another 13 days. So we had 21 days of studying, and we've done 9 of those days, and we've got 21 days of studying. Getting my math wrong here. We have it's day 9, and we have we have 13 days left. So we had 22 days of studying, and we've done 9 of them. So we finished, we're like a little bit before the halfway point, and we finished all the lectures, or I finished watching all the lectures. So that means I'm in a good position now for going through the problem sets. The first 5 problem sets, we went through them a little bit fast. Now that I'm here in the class, I'm thinking that was maybe a little on the fast end, but I think it'll be good to review and go back through them, because I think a lot of those problems, even though I did see what the answer is, it was a while ago. So they would often, I could probably go through them again to convince myself that I understand the solution, just to do that active recall. So we're a little bit early, but if I look at the time, I've been sort of at this for 3 hours and 15 minutes. So it's a little bit more than I'm generally planning on doing in the afternoons and in the morning. So I don't think I'm going to push forward now into the problem sets or into doing some Feynman techniques. I'll just spend a few minutes kind of recapping my kind of high level intuition of what quantum mechanics is all about. And then obviously that's going to be deepened over the next 2 weeks of working with the problem sets, of doing those things. And then I'm hoping I might be able to, in addition to working through this exam, which I've already expressed few reservations about just because it's not from this session and it's only a practice exam, and I'm hoping that it's going to be suitable. But even if it's not suitable, even if we're not able to get that same quantitative feedback that I'd like to get, I think I'd like to do some kind of intuitive summary, because I really liked how this class proceeded in giving you this experimental setup and then giving you all this sort of understanding of the math behind it, so that it's sort of mathematically true that this is going to be that. But obviously for most people, they're not going to wade through that math. And I did want to go through that math because I think the math is in some cases what you need to understand why something would be true. If you don't have the right mathematical structure in your head, it's really hard to form intuitions about things if you've got the wrong picture. So I feel like I'm trying to develop that intuition, but then hopefully I can try to present some things that don't involve math and gotta give sort of an intuitive picture of what's going on. Obviously I'm not going to be able to do it the same way as like Stephen Hawking or someone who's written popular physics books. Obviously not a physicist, but I'm hoping I can show that in a short period of time, you can learn some quantitative skills, build some intuition, and then hopefully arrive at some basic intuitions, even if you don't have, the same depth as someone who's spent a whole set of time working on it. So I think, for me, if I'm just to summarize my current intuition, which is hopefully not as deep as it's going to be after spending another 2 weeks with it, I'm going to see more patterns and relationships after working through the problems of 2 weeks, is that the idea we're working with here, and you know what, maybe I'm going to show on this piece of paper so I can see here. But we've got, this is kind of a weird bluish color. Let me just see if I can adjust the blinds so that it's getting a good color balance. Looks like it's a little bit better. All right. So the whole idea, I think, before was that we had some kind of, well, we're putting in, let's say, kind of electrons that have this property. We're putting them into this hardness box, and they're going out. Maybe I'll separate them like this. They're going out here and here, and we have hard and soft like this. And the thing is that we know that if we put another hardness box in here, they will be all hard. But on the same time, if we put a color box intervening and then the hardness box, we get the split again. We get the 50-50, which is not what you'd naively expect, because if hardness was a property, a definite property of the electron, that, hard electrons are always hard and white electrons are always white, and this, if this was maintaining, then how should measuring this sort of unrelated property change things? And I think one kind of picture that I'm sort of forming in my head is, you can think of these, and like obviously it's going to be a little bit more complicated than I'm drawing here because we're just like the 1D case, but you can imagine kind of a one-dimensional string. And of course, if it were just sort of a single value of this wave function, it would just look like a wave like that, right? Like it would just have some kind of power in this direction. But of course, it's not like that. It's a complex number. So a complex number means two-dimensional, which means that there is some kind of rotation, and it kind of looks like a corkscrew almost. If we were looking at, let's say, this plane wave, it would look like this. And the thing is that if you were to measure this, the probability is just even at all points. But because there's this phase complement, if you add in a different wave, say going in a different direction, then these two waves sum together, even though they just look like they're even probabilities, might actually end up giving you something like this, right? because you might have this interference terms. So I'm going to have to draw these a little bit better because I'm trying to kind of express this overall 3D analogy. But you can see this superposition in my mind. The way of thinking of it is just the same way that you have superposition of waves on a string. That if you were to make this wave, let's say, and send it forward, and then you were to have maybe, let's say, like this wave and send it this way, there might be some point where you have kind of this superposition of the waves sort of overlapping each other. But the waves, the superpositions are kind of independent. They just keep going off from each other. So what we're having here is that this overall wave is taking these two sort of components, which are kind of in a normal electron, sort of stacked on top of each other. And it is pushing them apart so that these two things are, in some sense, physically separate from each other. But as soon as we put them through, we put this one through the color spectrum again, it is measuring it from a different perspective, and we're destroying that value. So I think there's some ideas here that are kind of tantalizing about what does the wave function, what does it look like as it's sort of moving through time? So when we're talking about like spin or these things, what is it actually looking like? So I think there's a visual intuition that I'd like to kind of perfect there. But I think just sort of naively, we're thinking about this, that the main difference between this and just sort of regular probability over states is that you have this complex value. So something that can have probability 1 in all space can have different phases which can interfere with each other. So you can have, you know, this and this neutralizing to 0, even though the probability of both is exactly 1 in space. And so the same thing with these different states is that you can have ones that that looks like it's normal, but then you can split them apart. So this is really bad. I'm doing this kind of spur of the moment. I think what I need to do is sort of prepare my thoughts and sort of try to find a way to articulate it better. But what I'm going to do is I'm going to break for today right now, and I'm going to work back on these problem sets, try to build that intuition, work on it. And then I might also spend some time, depending on how comfortable I feel with the mathematics, spend some more time kind of hammering down this sort of visual intuition so that I can get kind of a crisp picture that's not mathematical, but just sort of involving, you know, some kind of, I don't want to say geometric interpretation because we're dealing with, you know, a complex value in 3 dimensions is, you know, this sort of vector on a plane, but at every single point in space. It's kind of hard to imagine what that looks like. But I think if you can get some kind of intuition in that regard, then these sort of crazy experiments, they start to make more sense. They start to make more sense. So just even the uncertainty principle with momentum and position makes perfect sense when you think of momentum as being the frequency, but like to have a narrow position means that you have to add all these different frequencies together. So that just sort of makes intuitive sense once you have that geometric understanding. And so maybe I can extend that to include some of these other properties, and then think about like, what does that mean, or what's actually happening that allows it to evolve this way. So this is a very interesting subject. I mean, I feel like I'm at the cusp of really grasping some of these deeper ideas. I know that when, for instance, I was interested in learning quantum computing after, or around the time I was doing the MIT challenge, I was like, oh, I should take a quantum computing class. And because I didn't have a good grasp of this quantum physics stuff, I just didn't understand. I was like, I don't understand what the superposition means. I don't understand what you're doing with the superposition for the qubits. And I feel like I did fairly well in the computer science classes. So it wasn't a computer science problem. It was just me not understanding the physics right. So I'm going to start working on this. It's funny because I have finished this full booklet. So this is 240 pages back and front. I've made notes for here of all these things. So luckily, I've got a new notebook, so I can crack that one open and start working through things tomorrow. So, you know, I appreciate everyone who has been kind of dropping by to see what's happening. I don't know how many people are watching right now. For some reason, my dashboard doesn't show this. But in the case that you're watching this much, much later, or you just randomly clicked on a section from this video to see what he's doing, and you're listening to this segment right now, I appreciate you watching this, and I will be back at it tomorrow.